It's sick for people to hop on, doesn't it?
Yeah.
Well, let's give them some. Well, thanks for my name tag, April, I appreciate it.
It's for, in case you forget something.
Don't forget who I am.
Yeah, you blended really well.
Good to go?
People are still joining.
Okay.
Yeah. You're good? Yeah.
Hey to everybody in our live studio audience and hey, everybody on the interwebs, Tom Jolene here. We have a, what I call a basics class. We're gonna be doing a lot on terminal boxes and then some on silencers and fan coils and air distribution. We've got our new powerlifting regional manager, Elizabeth Turner here today. So welcome, Elizabeth. The first hour, well, we're gonna give, whether you're a contractor or an engineer, we're gonna give you some tools that are gonna save you potentially a lot of time when you're building your box schedules. However, we would like you to understand what you're building when you build your box schedule. So we're gonna cover those basics first. And then the second hour after our break, Elizabeth's gonna show you the tools that are available to speed that process up, which is, it's pretty impressive stuff that Price has put together with their Revit and Excel plugin tools. So you definitely want to know what you're building before you build it, but then it would be nice to build it really, really fast. And then our third session will have air distribution and we think silencers in a second. So we've got a lot of ground to cover. So thanks everybody for coming. And without further ado, Elizabeth Turner. Take it away.
Good morning, everyone. As Tom mentioned, I'm Elizabeth, Regional Manager for Price Industries. I've been with Price for about 4 years, spent most of that time in the terminal unit group. So I was an applications engineer for terminal units. I do have an engineering degree, so I'm not just a salesperson. As mentioned, we're going to spend the first little bit here talking about single ducts and fan power. So that's kind of where we'll get started. This whole section is going to be on sizing and selecting your single duct and fan power. I really did not fly up here to just talk at you for 3 hours. So I'm going to entice you to talk back to me with tickets, with raffle tickets. I've got some fun little prizes up there. And so
We love prizes.
Prizes, yes. If you ask a question, if you answer my question, I'll be handing out tickets all day and then we'll raffle some stuff off at the end. Please interrupt me. Don't raise your hand, just interrupt me and I will stop and address your
I
question.
have a question.
Yes.
What if someone's remote and they want to ask a question? We can send it to them, right? I'll send it to them.
Oh, send them
We're
a
willing
prize,
to
yes,
entertain
yes,
questions from our
virtually,
guest
yes.
audience. So that means you guys get to use your, is it the Q&A or the chat function, Tamara?
Either.
All right, use either, whatever you like.
Yes.
Sorry to
it's
interrupt
virtual. Can they hear that microphone and this microphone?
It's going on for that one.
Oh, okay. So if you didn't hear Tom virtually, yeah, send in your questions and we'll make sure you get swag as well.
Right.
I guess we'll go ahead and get started. Sizing single duct and fan power. Get past some of this nonsense about content here. All right. We'll start at the absolute very beginning. How do terminal units work and what are they actually used for? So in a space, let's see if I can get this little guy. There we go. All right. So in our modern day buildings, terminal units are used to create zones within our space. So inside of those zones, we can use a terminal unit to regulate the airflow. That could be our cooling load. Usually we're supplying fresh conditioned air from the air handler through our terminal unit. We're going to regulate that volume of air the terminal units. So we're modulating our cooling load as well as the ventilation air in the space. Usually a terminal unit will have a reheat coil on it, so we can adjust the heating load in the space as well via electric coil or hot water coil. And then kind of one unfortunate side effect of terminal units is that we are adding additional sound into the space. Some of the different sizing practices we'll look at today will kind of address acoustics and how to avoid adding too much sound into the space. With a video to play. Thanks. I've never controlled the PowerPoint with a mouse before. Yep. All right. I don't even know where my mouse is. Whatever. The absolute most basic type of terminal unit is a single duct box. Your single duct is simply a rectangular box with a primary air valve. Inside of the box,
There you go.
inside of the box, you do have a damper. So here through the box, we can see fresh air is flowing into the primary air valve across an airflow sensor. The damper is controlling that airflow, but it's being controlled by this controller. So your controller is kind of the brains of the single duct box. We're going to be measuring airflow, sending a signal to the controller, and then adjusting the damper. Again, the most simplest type of terminal unit, really all we're doing is changing the volume of air given to a space. This is your single duct box. Later on, we're going to look at fan powered boxes, which is a combination of this with a fan. So as was kind of mentioned earlier, we can use single ducts to create zones in our space. So in this big office building here, in the back corner, we've got one independent office, and we have a single duct up in the duct stream. So that little blue box there is a single duct terminal unit. It is going to be changing the volume of air into that single independent office. Now, how are we actually getting any of this air to move through the system? Pressure is our most important piece to this puzzle. We can't get any air to flow through our system without pressure. Now, if there are any engineers in the room or online, you're probably looking at some of these equations, maybe having awful flashbacks from, from university. I'm not going to teach you about Bernoulli's principle, but what we are ultimately going to get to is a pressure equation. Again, pressure is the most important piece to our air system. Can't get any air to flow without pressure. So through some deductions with Bernoulli's principle, we're going to end up with this equation right here. Total pressure equals static plus velocity pressure. Static pressure and velocity pressure are the two main components to our system. And how do those play into effect? So the first is going to be your inlet static pressure. We look at a terminal unit installed in a run of duct. For example, we can look at this box over here. The green duct is your inlet duct. This is coming from our air handler. This is where we're going to be measuring and finding our inlet static pressure. That inlet static pressure comes from your air handler. The fan on your air handler is pressurizing all of the duct downstream, and it is providing a positive pressure to the inlet of your terminal unit. We're using a damper to kind of hold back some of that additional pressure, but this is where our positive inlet static pressure is. Downstream of the terminal unit, so all of the red duct in this image, downstream is where we are measuring or creating a discharge static pressure. All of the accessories downstream of a terminal unit have some sort of resistance to them. Maybe it's straight duct, flex duct, we've got diffusers in this image, could be a water coil, silencer, turning vanes. All these different accessories downstream of a terminal unit are adding resistance to our airflow. The positive airflow that we have on the inlet has to be larger than all of the downstream pressures to get any air to flow down into our space. The final type of pressure, which is important, is minimum operating pressure drop. You're probably never going to see it actually called that on a schedule or in specs. That is the ASHRAE terminology for the pressure drop of the terminal unit. So down here, we've got the single duct box. The minimum operating pressure drop is just the pressure loss across the terminal unit. I mentioned earlier, we need to be concerned with the pressure drop of all those other accessories. Same thing is true for the terminal unit itself. This is another device in our duct system that has a pressure loss associated with it. So we need to make sure that we're sizing our air handler to overcome the pressure loss of all of those terminal units in the system. Again, the takeaway here, inlet static pressure has to be greater than the sum of all downstream losses to get any air to flow. So that was static pressure. The other piece to our equation there is velocity pressure. So static
You
pressure.
guys did a great job with this animation.
We have a wonderful marketing team.
Well, I mean, it does make it easier than looking at a catalog.
Oh, absolutely. So velocity pressure is directly correlated to our airflow through the box. Velocity pressure equals CFM. Now, how are we actually measuring that velocity pressure? We're using an airflow measuring device in the inlet valve of the duct. There are different manufacturers do it differently. They have different measuring devices. Some of the kind of historic older versions would be a linear flow sensor that kind of just goes on the outside of the duct. Maybe it's in a diamond shaped, maybe it's in a ring. Those are, they're okay, they're good sensors, they're economical, but they are not very good at picking up poor velocities into the duct. So something like this, which is called a cross flow sensor, when that image spins around, you can see the inlet a little better. We've got, we're mounted to the outside of the duct, but really all of our measuring is happening in the cross there in the middle. On the front face of the sensor, you're picking up total pressure. So again, total pressure, static plus velocity. We're capturing all of the pressure going into the inlet valve. Hidden on the back side of the sensor, you kind of see the little arrow right there. On the back side of the sensor, we're able to pick up a static pressure in the duct. There's no influence of velocity passing over the sensor. It's hidden in the back there. So what we're actually sending to the controller, a total pressure and a static pressure. But what we ultimately want to get to is that velocity pressure. Velocity pressure is very difficult to actually measure itself. So we're using that pressure relationship to find a velocity pressure, which can then be correlated to our airflow. How are we doing that? We're doing that with calibration curves. So this calibration curve is something that a test and balancer would use on site. They are measuring the velocity pressure through that cross flow sensor and then correlating it to an airflow with constants. I know this graph is really difficult to see, but essentially all we're doing is just relating the velocity pressure to an airflow with set constant lines. So this is how we're balancing the single duct in the field. And then usually they're doing a downstream measurement, maybe with a pitot traverse, as a kind of second verification on the velocity there. So that's how we're using that airflow measuring device to find our airflow. All right, so now we're going to look at how do we actually size single duct inlets to achieve what we ultimately want in the field. So this is usually a job of the engineer when they're setting up plans. They're going to be the ones to determine how much airflow we need in the space and then ultimately determine what size of equipment that we need. We're going to go through a bit of an example here. So we're looking back at that office building, but we're going to focus on this one room. We're going to call this kind of like a multi-purpose conference room, and that will eventually get us to the final airflows that we need. So, associated with every type of space, there's always a square footage and a number of people that we're sizing that space for. When we're starting to go through and picking our airflows, we need to be concerned with a couple of different points. Our maximum cooling airflow, at maximum load, how much cooling airflow are we going to need to provide to the space. We're concerned with our minimum airflows because we need to meet minimum ventilation requirements in the space. And then Heating would be another concern for this example. We are only going to be looking at cooling. So an engineer would use load calculation software and determine what the total amount of cooling load would be needed in the space. And then we can go about finding our airflow. So with this simple heat transfer calculation, if you're an engineer, you've probably seen something like this before. We know what our load is in the space. We know our target delta T. So what is that resulting airflow? Through this equation, we can see that our airflow is about 690 CFM. And we always want to be sizing the inlet valve to result in a velocity no greater than 2,000 feet per minute. 2,000 feet per minute is kind of the threshold for where an inlet will start generating its own sound. So we have our airflow, but we want to pick an inlet size that keeps us less than 2,000 feet per minute. Little bit of circumference or area calculations. With that determined airflow, we can see that an 8-inch inlet valve would keep us below the 2,000 feet per minute set point. Now, just because this is what the math shows us, we need to check with a manufacturer's catalog to make sure that that's actually possible. So here's an example of a screenshot from a catalog. We can check that size 8. We can look at the size 8 inlet valve here. The manufacturer is recommending that max airflow be, no greater than 700 CFM. And again, that is our 200 feet per minute point. So sending 690 CFM through size 8 box will keep us below that 2,000 feet per minute. Kind of just a double check there through the catalog. So we've sized now our inlet valve for a maximum CFM, but we need to check the minimum as well. We need to make sure that airflow readability and controllability will be possible at those lower airflows. So where are we getting our minimum cooling airflow? Minimum cooling is always your ventilation rate in the space. ASHRAE 62.1 gives us equations or factors to be able to determine what that minimum ventilation load is. So for a conference room of this size, the ventilation rate per person is 5 CFM. We can compare that to something like a school classroom. In a school, they require 10 CFM per person. In an office building with adults, 5 CFM per person. ASHRAE doesn't care about adults quite as much as they do children, but you can just see that those ventilation loads are going to change based on what the space is. So with our 5 CFM per person, we also have an airflow for a square footage. So we've got the people ventilation load, the square footage. From there, we can determine what that minimum airflow is. 80 CFM comes out of that equation. So again, we need to reference back to the catalog to make sure that our size 8 inlet valve can actually achieve this range that we're trying to meet. So we've got our range here, 267 CFM to our max cooling 690. We double check the airflow range on that catalog. We can see that we're going to fit within the range. Now this minimum airflow that's set in the catalog for all manufacturers is based on a velocity pressure of 0.02 inches. It's pretty small velocity pressure. Again, that's what we're measuring at the cross flow sensor. In another section, I'll go through a whole discussion of minimum airflows, and why we're currently cataloged here and could we actually go lower. For the sake of this example, and sizing our 8-inch inlet, everything checks out. At the maximum end, we are staying less than 2,000 feet per minute, so we're not going to have any acoustic issues. And then on the minimum end, we're staying above the recommended minimum for the catalog. So we should have good readability, measurability, controllability on the airflow measuring station. Now, I have been in a number of engineers' offices where they tell me, yes.
Let me go back one, so,
Yes.
or 2 slides, I guess. So the minimum cooling was 80 CFM.
Mhm.
How did you get to 267 on the next slide?
So this is 5 CFM per person, 10 people.
Okay, that's
Square
B,
footage.
That's your outside air.
that's your
Is ADC,
ventilation
right?
Right,
rate.
this is ventilation,
Okay,
so then 30% of.
okay, because
total
it's 70,
airflow Is ventilation,
okay,
yes.
Oh, because you're 70-30.
okay, that's
All
where I
there,
was
yeah.
missing that
Yes.
part, okay.
Yes. I jumped slides, it was also like, wait, why did that airflow change? But I'm just gonna keep rolling.
I'll never notice.
All right. So I've been in too many engineers' offices when they're sizing single ducts and they tell me, we'll determine what it needs to be and then we'll just upsize it to make sure we're safe. That could be problematic. Sometimes it is okay and you are on the safe end, but depending on what those airflow ranges are, you could actually be making a bigger issue. So if we are oversizing an inlet valve, for example, in that last example, if we went to a 10-inch inlet, we are adding larger ductwork to our building. So if we do that for every single box, we've got larger ductwork, increasing cost and potentially labor. If we were to jump to a 10-inch box, our damper is now going to have to maintain a more closed off position. We've got a larger valve with the same amount of airflow going through it. So we have to modulate that damper back to really control down to that airflow. When we're sitting in a closed off position, like that top picture there, we have less range and less controllability, less turn down, it's just a little bit tighter of a range we're trying to control to, which is more difficult. We also have lower velocities when you're pinching off that valve. You've got lower velocity pressure, and again, it's a little bit harder to measure. And then finally, if we have an electric coil on this box, with those lower velocities, it's going to be a little bit harder for our pressure switch to close to run the electric coil. So oversizing could be okay, but you could run into a scenario, go back here, where we jump to the next box size and maybe we end up out of that range. So something to be mindful of if your company standard is just to automatically upsize inlet valves. A different solution to upsizing the inlet valve is maybe just upsizing the casing. A lot of people like to increase their box size for acoustics and capacity instead of just airflow measurement. So there is the option to keep your inlet valve size the same. Maybe we stick with that 8-inch inlet, but we increase our casing size to a size 10. That allows a bigger casing, which is less sound generation, and a bigger casing for a larger coil. So we can get higher capacity out of the coil if we're running the same airflows.
Does that screw with AHRI at all? You're allowed to do that, I assume. Everybody, I mean, we all do it.
Yes.
It's
Yes.
necessary part of the job, but I just wondered about testing.
So it's not a certified point. This box would not be a certified point that goes into, this catalog.
Yeah.
But the performance is still tested per AHRI standards.
We wouldn't want any engineers to do anything illegal.
Legal.
Shut up, Tom.
The engineer police are gonna come out next.
Are there any questions so far on single ducts, airflow measurement?
Does everybody get the whole, when the damper is nearly closed and then you open it a little bit, it doesn't really control all that well? It's like a quick opening percentage of butterfly damper thing.
Yeah, most controllers and actuators are not smart enough or high tech enough to, control these little percent changes. If you were to shrink that valve a little bit, now we're operating in a range that's kind of a larger sweep than this little guy is. You'll have less fluctuation and bouncing with a smaller valve.
It doesn't sound like a big deal till you're system's not controlling
Right,
and your VAV boxes are kind of hunting all over the place.
yeah,
It's like,
hunting is.
wait a minute, what's going on? Oh, you oversized your box. Ah, that's nonsense. Couldn't be.
Nonsense. I kind of alluded to this earlier. I'll do a quick discussion on reduced minimum air flows. Tom and I had a brief discussion about this yesterday, and maybe not in this market, it's a big topic of conversation, but especially along the coast right now in your super energy conservative markets, Seattle's a huge one. Reduced minimum air flows is a big topic of discussion. Everybody's trying to bring their air flows down and save energy as much as possible. But how does that concept actually interact with the manufacturer's equipment? So again, why is this a topic right now? We want to save money on just be conservative with energy in general, but then also save money on the building operation. LEED accreditation could factor into this, or even state codes. So here's a little kind of note on the Washington State Code. I mentioned Seattle is really strict. Their energy requirements is 0.12 watts per CFM in deadband. So for fan powered boxes, we're having to turn down fans really, really low to make sure we're meeting that code. And then demand control ventilation. DCV is becoming really popular now, especially in variable occupancy spaces like this auditorium. 90% of the week this auditorium is probably empty, so we don't need to pump it with a lot of fresh air. But when 20 of us are sitting in here, we do want to increase that fresh air. So running demand control ventilation and having those high turn down rates on the ventilation air could be important to save energy in a space like this. So we're seeing this trend continue, and turn down, lower ventilation rates are going to continue to be part of the conversation. If we were to run demand control ventilation in a conference room like this, what would that look like? What do we actually need to take into account and consider before designing a space like that? So ASHRAE did a research report on this, research report 1353. It's online if you ever get bored, want to fall asleep and want something to read. You can pop it open. And what they ultimately found in this research report, the whole point of the study was to figure out, can we actually turn down boxes below current manufacturer's minimums? What they found is yes, you can. You could turn down pretty far. So here we've got example of turning down to 101 CFM, turning down to 74 CFM, and even 49 CFM. So really, really lows. Look at the velocity pressure here. All manufacturers catalog down to 0.02 inches, 0.02. So you can see how low we're getting on the velocity pressure, all the way down to 0.003. Really small velocity pressure across that sensor. ASHRAE concluded that you can get those readings down to plus or minus 5% or you're still getting an accuracy plus or minus 5% by turning down below recommendations. Sounds a little bit too good to be true, and it kind of is. There's a lot of caveats that resulted in these findings. So what was required to get there? We had to have perfect inlet conditions. We had to have those 3 equivalent duct diameters of straight hard duct into the VAV inlet. And in the room, we've got a couple. How many times are you actually either installing or designing with straight hard duct into an inlet valve?
Always.
I hope Tom always is.
Always.
Usually people laugh at that because they're like, no, I never do that much space, or yes, I'm gonna put duct on there. So 3 equivalent duct diameters. We also have to use a specific type of controller on that damper that can measure velocity pressures down that low. Most commodity modern day controllers actually can't even pick up velocity pressure that low. So you have to use a specific type of controller. The system had to be balanced at that low operating point. And usually you're only balancing to a maximum. And then finally in this report, they were auto zeroing between every single reading. Most systems are not designed to auto zero daily, especially not hourly.
So you're using like an Ashcroft kind of a automatic auto zero, like a $800 pressure transducer kind of a thing.
Basically, yes, yeah. They, I mean, again, this was a research report, so they were using the best of the best equipment to run it. And then you also have to have a minimum damper position open of at least 25%. So even at that low airflow of, we were at 49 CFM, you had to be 25% open. Which means our pressure cannot be super high. If we're pumping 3 inches of pressure to that inlet valve, we're not gonna be able to be at 25% open. So in order to get these results, run this accurately, we had to reduce the pressure has to be reduced to less than 1 inch. Again, it can be done, but you gotta have all of these other things in place to be able to get there. The biggest takeaway, if you want to try to accurately run systems at low velocity pressures or low airflows, keeping that inlet static pressure down below 1 inch, closer to the 1/2 inch, 0.75 inch range is gonna be ideal and what's gonna help get you there. Yes.
As more markets are moving towards this energy conscious, like what we're looking at here, will that affect how spaces are designed? Because will you have to sacrifice being more energy conscious for being able to sufficiently heat and cool a space if everything is turned down much more?
Ooh.
That's a great question. Yes, I would agree with that. Now you are still only turning down for ventilation, so this is not our max cooling, right? But I am seeing a lot more control strategies change where there is true VAV, we're doing a lot of modulating and changing. So right now I'm seeing it more on the control side than just straight room design.
Oh, okay.
Yes. But that could ultimately play into, even just your diffuser selection, because some diffusers work well at those low flows and some work horribly at low flows. So yes, equipment selection will need to be changed for running those lower flows. Do you have anything you want to add? You looked like you wanted to say something.
Well, it's almost like all the people in the building can run from one side of the building to the other side of the building. But, that would, I don't know, it seems like if, like we talked about yesterday, if the fan is driving the building, you can only turn down the fan so far. So I don't know. It seems like a lot of, maybe there's something I just don't know about it.
Well, we might start seeing more units with fan arrays so that, you can not just turn one single fan down with a VFD, but you might see multiple fans within air handling units with multiple VFDs so that we can achieve very, very, very low airflows. And that'll be coming to Wisconsin hopefully soon, where we start to see 62.1 and more of these aggressive energy saving methods. So
Fan arrays, I can say, are becoming huge.
Oh, wow.
You tripped into the conversation.
That's right. I haven't seen a lot of people just shut off the fan array fans,
no,
other than for service. It's usually the whole thing runs.
Yeah.
And then they just run it like a regular old VFD kind of a fan.
yeah, I don't know if they're really looking into
I don't,
in-depth control strategies for
I
those.
don't
ones
see
yet.
them knocking down the bottom row because you still need coil coverage, so.
Yeah,
I don't know. Then you gotta circuit your coils differently, so it'll be interesting. I don't wanna be the old guy who says, well, it's not the way we do it. It's like, slowly shake my cane, but
You're usually the one up in front of everything, so
yeah.
you gotta get on board with this.
All right, I'll work on it. I'm embracing my age here.
All right, system effect and installation conditions. I've touched on this a little bit. The way that we're installing equipment is big and it's important, and it could ultimately affect the performance of the equipment. So system effect as a whole is the impact on our system, on our fan, on our airflow measurement that results from improper movement of air through our duct system. So for an example here, we've got really nice airflow. As soon as we turn that tight elbow, we're going to start getting some localized velocities on one side. This is one isolated example of system effect into a single inlet. But if you carry this for installation through your entire system, those little inconsistencies will continue to have a negative impact on your entire system. So on the inlet, just like what we saw, if we've got tight elbows on inlets, maybe we have sagging flex duct on inlets. On just that particular box, we're going to see localized velocities that will ultimately result in poor airflow measurement and control. So a crossflow sensor can compensate a little bit better for this, but if you've got another type of sensor, it's going to be picking up really high velocities on one side of the duct, but it'll be reading nothing on the other side, and it's not going to be very good at compensating for that. And then system effect on the discharge. So here we've got a fan powered box and a tight elbow on the discharge of the fan. That elbow is going to add additional static pressure resistance to the fan, causing the fan to have to operate at its upper position instead of kind of in its middle range where it likes to be. So both on the inlet and the discharge, we can kind of see effects of the equipment and its operating point. What is the actual way to do this? ASHRAE 130 is the method of test for terminal units. So all of the catalog data is tested in this very nice configuration. ASHRAE 130 tells us that we have to have 3 equivalent duct diameters of straight hard duct on the inlet valve of the terminal. And then on the discharge, we have to have 2.5 equivalent duct diameters of straight hard duct on the discharge. Now, again, you're usually probably not going to see this. Engineers don't often have that much space. Contractors don't have that much space and might not install it if the drawings are laid out that way. So this is how all of the catalog performance is measured and tested, but on site, again, you might not actually get here. So what can we do about it? Well, I kind of alluded to this, but the crossflow sensor is kind of your best friend in a scenario of poor inlet conditions. Now, this is only looking at the inlet, right? Because we don't have a sensor on the discharge. But in our lab, this is what this image is here on the right. In our lab, we've actually mocked this up and tested what are the effects of putting a hard 90-degree elbow directly on the inlet of a terminal unit. The crossflow sensor did an almost perfect job at compensating for it. We can see the actual airflow versus what the crossflow sensor is measuring in that graph there. We were able to maintain plus or minus 5% of that reading, even with a poor inlet condition, even with that hard elbow. There was some adjustment required on the K factor. So at test and balance on the controller, we had to set a constant in there to compensate for it. But as long as we were tested and balanced correctly from the beginning, we were able to maintain that airflow accuracy. Now, why is this possible? I wish I had another image of my crossflow sensor. It'd be annoying real quick. In your crossflow sensor, you've got 4 legs. But what's most important here is this center little component. This is a center averaging chamber. So it's a fancy word really just for an air pocket. It's kind of funny. I worked at Price for like 3 years. I didn't actually know what was happening in here. So I popped one open and it's just an air pocket. But what it allows the pressure to do, we're collecting 12 different ports, collecting through 12 different ports. All of those pressure measurements and reading are going to eventually find their way into this center chamber, and they will all average together. The average is what's actually getting sent out to the controller. If you have a linear flow ring, maybe one that's a diamond shape that doesn't have an averaging sensor in the middle, that's how you're going to result in poor readings or measurements because those pressures aren't actually measuring together. If you've got pretend this is a linear, whatever port is up here is going to have a higher influence on the reading than maybe the one down in this corner. So Because of that center averaging chamber, we were able to maintain the plus or minus 5%. There. There are a number of manufacturers that have a crossflow sensor, but not everybody does. So specifying a terminal unit with a crossflow sensor is important and will help kind of maintain integrity throughout the building. Are there any questions on this?
How about our studio, or how about our remote audience? We haven't had any questions from those guys yet.
In the chat there? No,
All right,
probably sleeping.
no, watching intently.
Watching intently. All right, we will get away from single ducts and start talking about fan powered boxes now and fan selection. Now this is not your kind of duct mounted fans. Again, this is still a fan inside of a terminal unit. So we have an inlet valve, but we also have a fan. Your two types of fan powered boxes are a series and parallel. At the end of the day, they both do the same thing. It's an inlet valve and a fan, but you're controlling them differently. So both types of units have a motor blower assembly. They both have an inlet valve. So this is what's ducted to our air handler. And they both have a return air opening. This is where we are inducing or drawing air in from our plenum. Now, what actually makes these boxes different is their configuration. So in the series box here, this is called series because our inlet valve is in series with the fan. They're in line with each other. Your fan is located on the discharge in a series box. That is very important. In your parallel box, our inlet valve and our fan are in parallel with one another. They're in parallel. They're not in line. If we were to chop off this fan side of the box, it operates just like a single duct. It looks like a single duct. So they are kind of two separate components coming together side by side, just like a circuit. How do they operate differently? In cooling, for a series box, because our fan is on the discharge, our fan always has to be running to provide any air to the space. So in cooling, our fresh air through the valve, our cooling airflow, will match the fan flow. We're just gonna send everything downstream. Essentially, this is acting like a booster box. Say we've got 1,000 CFM through the valve, our fan is running at 1,000 CFM. We're just gonna continue to move that downstream. We don't have to have high inlet static pressures on this valve because our fan is acting as a booster. So it allows us to take our air handler, kind of turn the fan down a little bit because we don't need such high pressures on that inlet. Now in the parallel box, in cooling, we're acting just like a single duct. So again, we don't have this fan section here. The fan is off, it's not running. We are pushing air through this valve and it's going straight down the discharge, just like a single duct box. Because of that, we do have to have higher inlet static pressures on this inlet valve because it's just like a single duct. The fan gives us no assistance in cooling. If we switch over to heating, now we're going to start bringing in some of that warm plenum air. In your series box, our fan is still running because the fan always has to run in the series box. The only difference is that we're changing the air through the primary valve. We're in heating mode. We're bringing our fresh air or our cooling down to a minimum. We're down at that minimum ventilation. So we've got a small amount of air pulling through here. The fan is inducing the rest of the air through this return, which is usually open through our plenum. So in my earlier example, our fan was running at 1,000 CFM. This valve probably dropped to about 200 CFM. The rest of that air now, 800 CFM is what's getting pulled in through the return. So usually your fan is always staying, at the same CFM. We're just changing the ratio of fresh air to return air. The parallel box in heating, now we energize the fan. The fan is what's going to induce our air through the plenum. And these two streams are going to mix inside of the box before going downstream. Our fresh air is still turned down to a minimum, but our fan has to energize to draw anything else into the box. Any questions on series versus parallel, how they operate? experts, fantastic.
What do you see more of now? Cause it used to be that series was more frequently used, but now it seems like parallel is more considered more energy efficient.
Other way around, yeah, so parallel was very common for the longest. They were pretty even with each other, and now series is kind of taking off because of its energy efficiency. So previously with PSC motors, so your old style, not really adjustable PSC motor, the parallel box is more efficient because your fan was not always running. You only ran the fan and used that energy when you needed it to. Whereas in the series box, you always had to run an inefficient motor. Nowadays, with ECMs, or EC motors, the series box is more efficient, even though your fan is always running. Where you're actually losing efficiency on the parallel box is leakage. So when we're in cooling and that fan is off, this is a pressurized plenum, and this is almost negatively or neutrally pressurized. So air is going to leak out through this fan opening here. ASHRAE's measured it anywhere from 10 to 15% leakage. So now with ECMs and fan efficiencies kind of out of the picture, leakage is what drops the parallel box down. So I see a lot more series. There are some markets that are parallel and will always be parallel. For example, the South, Georgia and Florida pretty much only sell parallel boxes because our heating load is little to none for most of the year. Along the coasts, series boxes are the only thing you see.
And are you seeing the case that using series fan powered boxes versus straight just single duct boxes is actually as a system more efficient?
Using series boxes instead of single duct boxes
Yeah.
as a system are more efficient. My first thought says yes, but I don't have hard numbers to back it up. I want to say yes, but I don't have a study for you.
In terms of efficiency,
Yeah,
Yeah, system efficiency.
because you can turn, if you have all series boxes, you can really reduce your air handler. Now you have dozens of booster boxes. Which will ultimately result in less duct leakage because your pressure's lower. And then you have the variability on the EC motor at the fan powered box
Right.
to then again change fan volumes. Like we could debate this for a while.
I'm just kind of curious what to see.
Yeah.
We mostly see single duct terminals, but maybe there's a case.
Okay, motors. So I've kind of already alluded to this. There are two different types of motors that you could put in a fan powered box, PSC or ECM. If you're an engineer listening to this, I hope you are never designing PSC motors, unless you are retrofitting a building that already has PSC motors. They are your old style, kind of historic motor that is very much being phased out, primarily due to its efficiency. So PSC motors only have an efficiency of 20 to 70%. They are more efficient at their top end. So if you're running it at its kind of max range, the top 25%, then you're going to get to 70% efficiency. That is the highest amount of efficiency you'll ever get. If you are not running it in that top range, you're more like 20 to 50% efficient. The way a PSC is working is it's chopping down the electrical wave and turning it into heat. So you have a lot of heat loss with a PSC, which is where you're dropping your efficiency. Also, if you're running at lower flows on the PSC, sound is usually a huge issue. They hum a lot. They make a lot of noise. I've been on too many job sites where that was the issue, is that they were running it too low and they were noisy. You also have to, when sizing and selecting with the PSC, be even more mindful about your static pressure, because we can see in this fan curve here, the fan curves drop off really quickly as our static pressure starts to increase. So, you know, you're throwing water coils, maybe you're throwing silencers on the boxes, pressure's rising, and that possible airflow is just gonna keep dropping. Don't use PSCs. Instead, use ECMs. Your efficiency is much higher, always in the 70–80% range. So you're staying at a higher efficiency through the entire range of the motor. And it's kind of just got a longer life with a much higher turn down. So for example, here you can see, you know, we can turn down from 1400 CFM all the way down to 100 CFM. You have the variability wired up to your BAS system and remotely change the speed. That's not the case with PSC. It's a set it and forget it. Yes.
Are you gonna touch on the difference between pressure independent motor programming and high turn down flow?
I absolutely will, just for you. So
Tamara, I don't see that question.
There is a question in the chat from Jonathan Olson. I think it's directed at Tom. When Wisconsin adopts the 2018 IECC, the revised turn down requirement 20% and the maximum heating airflow 50% will likely result in the use of more fan powered boxes or oversized single duct boxes.
Oh, well, there we go. So Elizabeth, here's a good opportunity to expound. If we are at 20% airflow. Well,
Say that again, before it.
sounds like 20% minimum flow instead of, I think normally it's like 33. And
Okay.
heating CFM is at 50%. What new and interesting challenges, you don't have to answer that now, but we should be answering it before we go today. Because those are fun conundrums, part of which you can address in the air distribution section.
I'm not understanding the question. If we have a lower turn down now at 20% instead of 33%.
Yeah, well, the heating CFM is gonna change. Usually it's like half, right? Sometimes it's even lower.
Mhm.
And then what was the other part?
Maximum heating airflow will be
The
50%.
maximum heating CFM is gonna be 50%. So if you're 800 CFM box and cooling, the max heating is gonna be 400. You almost need like two different diffusers.
Yes.
So we can talk about that. So Jonathan, that's an awesome comment. Thank you. And we will tackle some of that a little bit later. It sounds like series boxes are on their way.
Okay, yeah, we can definitely talk about that. I wish we were all at Price and I could show you our FlowViz room and we could actually show that in a diffuser layout. But I'll do my best to show with videos on a slideshow. Okay, back to fan curves and different motor programs. So Ryan pointed out that this ECM fan curve here has a ton of different lines and two different motor programs listed on it. Might be a little hard for you all to see, but inside of this red box here, we have one program called Pressure Independent Flow Program. Pressure Independent Flow Program actually allows an animation for this. Look at that. Pressure Independent Flow Program allows us to hold a consistent airflow regardless of changes in pressure. So this fan line right here, you can see how it's angled. Inside of that red box with that motor program, that line goes vertical. Let's see if I can use my little tickets here. So our fan line will ultimately look like this. So if I'm at 1200 CFM, it doesn't matter if my static pressure changes from 1/4 of an inch all the way up to 1/2 inch. The motor's going to compensate and hold that pressure. Again, for my engineering students, PID loops. Ring a bell, maybe? Using a PID loop to compensate for the change in pressure and then change our airflow. So up to 1/2 inch, we're gonna hold that same airflow. A really good practical application for this, imagine if you have a filter on the box. Over time, the filter is gonna be loading. That filter pressure drop is gonna change, it's gonna be variable. So we can still hold a consistent airflow even if our filter's loading. That is pressure independent flow. The other program here is the bigger red box, high turn down flow program. This high turn down flow program, exactly as the name says, it allows us to turn the motor down to 100 CFM. Doesn't matter the size of box, doesn't matter its top end, we can always get down to 100 CFM. I say 125 to be safe, but you're at about 100. The downside is that your fan airflow will track in that diagonal line. Less than the PSC, you can see it's not quite as kind of tapered off as the PSC, but we do have some reduction. As that filter's loading, as our pressure's increasing, we will see a little bit of a reduction, which ultimately will change kind of that top end possible airflow. Both programs have their places, both are really useful, but it is something that does kind of have to be determined before ordering the equipment. Does that answer your question? Are there any more questions about it?
No, normally in specifications or schedules, we don't see that called out anywhere. Is there kind of a standard that we can determine beforehand?
Yes, my rule of thumb is always go pressure independent unless there is a scheduled airflow lower than that pressure independent range. So the schedule should note that somewhere they're gonna need a big turn down on the fan. If you're dropping below, in this case, that 300 CFM, then I would go high turn down. Otherwise, default to pressure independent.
I mean, in worst case scenario, can you go all the way up to 0.6 inches in static pressure with the high turn down?
With high turn down, yes. Yep,
Okay.
0.6. Anything above 0.6, you can. The fan curve takes off. It starts to
Yes.
level out
Yeah.
really quick. So 0.6 is your safe end.
Mhm.
And then if you need to go above that, then we start looking at lab data. And then as far as sizing airflows, we typically recommend keeping your fan size between the 50 and I usually go up to about 80% of its range, of its top end range. We don't want to be sizing a fan to operate way out here. It's gonna be loud. It's literally screaming. And then you lose any adjustments really. Yeah, you have no more room in the fan. You put a water coil on it, well, immediately you're outside of that box, right? So try to stay within at least the 80%, of its kind of top end, usually down to 50. We also don't want to be sizing. It's a little easier with ECMs. It's okay if you're on the lower end, but you might as well just drop down a box size at that point if you can. So here's just kind of a summary of ECMs versus PSC and really where you're getting your savings. So again, you get really high turnout PCMs, they're more efficient, and ultimately you're going to be saving money. So the lower line here is your ECM operating cost versus your PSC operating cost. All right. Any questions?
We were gonna take a break at some point.
Yes.
Have we asked too many questions?
No, never. You did not ask too
Just
many
making sure.
questions. I think I want to skip the electric coil and water coil
We agree.
sections. I'm going to, there's a lot of numbers on here, like. This is a cool animation though. Laminar versus turbulent flow. I'll keep going.
I think we wanted to take a break somewhere in here, so are
Do you
we?
want me to, we can either do software, break, and then have Mauricio jump in, or we could break, then I could do software straight to Mauricio.
I think we should break, because the hour and a half, people tend to peter out, so we'll be back here, it's 10:01, we'll be back here at 10:10.
And 10.
And Mauricio, if you're listening in, we'll just start a couple minutes later than you expected. All right, see you guys in a couple minutes. And there's plenty of, there's like a egg bake or something, so if you guys are hungry,
Yes.
please dig in.
It's good.
Freaking the Dave Chappelle skit. Charlie Murphy.
We back on, Tamara?
Yeah.
Okay, good.
We're live. Everyone's fancy flyers. All right. So for about 20 minutes, I'm gonna demo some software. I know software is quite boring. I will try to go through it pretty quickly and kind of just give an overview of how it could help you as an engineer in your workflow. The flyer in front of you is kind of the flyer for these software tools. So you're probably gonna forget everything I say. There are 2 QR codes on the front here that bring you 2 10-15-minute videos demoing the software. So you could watch it again, you can send it to a colleague, etc. And then on the back side is a QR code that gets you to this landing page, which is where I'll start. This landing page on our website here is the kind of page for all of our engineers' tools. We do have 3 different tools, Toolkit for Excel and 2 different tools for Revit. Now, our whole goal with some of these specific softwares was to create engineering software that fits into your workflow, instead of asking you to go to a different external software. Is anybody in the room familiar with Price All-in-One? And every rep's gonna raise their hand. Any of my non-Airflow reps familiar with All-in-One? Yes, great. Awesome, I've got one. Okay, what do you use All-in-One for, if I can ask? Perfect, okay. So All-in-One is fantastic, it's been around for a very long time, but it, it is an external software you have to download, it updates.
It's a massive file.
It's a massive file. Can be kind of cumbersome if you're not used to it. So we have built new software, again, trying to fit into your workflow. Assuming you have Excel on your computer, probably Revit. You guys design with Revit? Okay. So the Excel toolkit's the first one I'll touch on. I'm very glad you do VAV selections and all-in-one. Hopefully this tool will help kind of make that a little bit faster. So the Excel toolkit is a plugin for Excel that helps you build out terminal unit schedules. It has all of our catalog performance, just like you would get out of all-in-one, but it's in Excel. A little bit easier to use and navigate. So from that website landing page, if I were to click download here, it brings me straight to the Microsoft Store. And it is just a plugin, so it's free. You can click get it now. And I will end up with this extra toolbar at the top of my Excel page. It's the Price Industries toolbar. And I mentioned it helps us build out terminal unit schedules. There's some GRD in here. We'll talk about that later. The primary function, again, terminal unit schedules. So I'll run it through an example real quick of a single duct schedule. Maybe we'll throw a hot water coil on it and we'll solve for leading air temperature. Go ahead and click generate schedule. Now this first feature here will give you a massive pre-built schedule with every performance parameter you could possibly need. Engineers are probably not putting this much detail on their specs. So again, it is still just Excel. I could go in and remove columns, move columns, kind of customize it to make it what I want. Heating min and max is not really something that's used in the United States, so I'll just get rid of that. I know for my water coil, I'm only using water, not glycol, so I can hide that. Maybe we don't need all of these pressures. I'm only concerned with coil pressure drop. I can hide those. Again, you can kind of customize it, but it is giving you everything you can need up front. I'll run through a kind of quick example of just one line so you can see how the performance populates. All of the blue cells are your inputs, the yellow cells are your outputs. So we'll select a sample here, zoom in a little bit more. Let's say my max is 800 and we always design for 20% minimum. So I'm 0.2 times my max, still Excel. I can use my normal functions here. Maybe reheat is 50%, 0.5 times fully max. Inlet static pressure, usually about 1 inch. Downstream, we'll say 0.25. I'm gonna scroll all the way over to my water coil section here. Primary air temp, usually 55, 75 return is pretty common. Entering water, start with 180. standard casing, standard coil. We kind of talked about oversized casings earlier. You can look at performance in here with that. Start with one row and try to target a leaving air temperature of 85 degrees. So here pretty quickly, I've got all of my performance already calculated in a schedule view. I'm sure you all are not specifying to 8 significant figures. We are working on an update to get this brought down to more reasonable numbers. I'll just leave it for now. So we have our fluid flow, heating capacity, leaving water temperature, fluid pressure drop, all of our water coil performance. It is also calculating our sound. So we've got our discharge and radiated NC levels, our unit weight, and it's auto calculating our unit size. I did not specify an 8-inch inlet. It chose an 8-inch based on my airflows that I fed it. If you have company standards, you can absolutely override that. If I change this to, I just literally typed in 10, it would fix all the water coil performance and update it. So it has a function to auto size, but you can remove that. And then we have our pressure drops over here. We have our coil pressure drop and our operating pressure drops. So full complete schedule with catalog performance right there in Excel. Pretty quickly, I could kind of fill out this entire schedule, with airflows for my specific project and get all of the coil performance. Now, this big pre-built schedule is easy. It's simple. If you have someone who is not an Excel wizard, this is kind of nice. But if you have someone who is good at Excel, you can kind of make it even more of what you want. For example, this schedule here was an engineer's template that I went and visited last week. I matched their template completely in Excel, so it only has the performance that they need, but it is a working schedule. If I want to target a leaving air of 80 instead of 85, I can change to 80 and you'll see the entire schedule is going to update there. Maybe one of my blocks, we changed airflows on the project, so I could just drop that to 800, see it recalculate. So this is a little bit more useful than maybe that big pre-built schedule because it's super customized for your firm. How did I build this? You can see in this pre-built schedule, you guys may or may not be able to see, there are functions up in the top toolbar here that are referencing all of the other cells. So I click on fluid flow, we can see we're calling for all those other cells. You have access to these functions outside of this pre-built schedule. So how I built this customized one, I can call and add in, I can add in these functions for the Price Industries Engineer Toolkit. I have access to every single performance function I could need, and I can bring it in and customize it myself. And I'm not expecting anybody here to walk away knowing how to do this. Our team is currently building a lot of these schedules for engineers who are interested. But if you do have someone who's really good at Excel, they could probably take this and do way more with it than we would have ever even expected. Are there any questions?
So what's the upside for the consulting engineer if they are already using, so most engineers have, let's say they use train trace, they're getting their minimum airflow, their max flow, and their MBH load out of Revit or whatever whether it's trace or whatever. And then they dump that onto a schedule and they're done. So what would be the upside of using this versus just the way they've been doing it for the last 20 years?
The upside of using this is that hopefully it's faster. And it's in Excel, which everybody kind of usually already has. It is cloud-based, so if there's any changes made to performance, it's going to continue to update live. As if we make changes, it will update in your file. You're currently using Price All-in-One. How do you haven't even touched this, but just at first glance, how could you see it comparing to All-in-One? Okay. Maybe just faster. Yeah.
Well, and the thing about this engineer's schedule, which, God, I hope they don't use 4 rows very regularly, But that happens. So when you use just your regular old, maybe you can talk about this. When you use your regular formula to calculate GPM and MBH, it doesn't match the catalog data. So
Yeah,
you
so
expand on that.
so the biggest benefit, there are a large number of engineers who are not using manufacturer software. Obviously, up until now, we've been trying to preach, use a manufacturer software, because if you are just using engineering heat transfer calculations, you're not gonna get exactly what the catalog will show. So at least using somebody's software will get you closer than those equations. There are a lot of engineers who are still just using Excel with their own pre-built equations. So if you're already using that method, changing to something like this, you're familiar with Excel, but now you have accurate lab tested data in that schedule instead of just the equations that you pre-built
With pressure drop. So
with pressure drop, yeah.
this schedule doesn't actually show the pressure drop of a 4-row coil, or now it's a 3.
Yeah.
But that's gonna mess with your system. I don't know why it's left, or maybe you just cut it out.
I matched what the engineers had already put on their schedule. So this is what they are specifying already. I could very quickly add coil pressure drop, air pressure drop into the schedule. It would take me 90 seconds.
Let's see it.
All right.
Set your watches,
Put me on
people.
the spot. So I'm going to add my function here, go water coil, that's water pressure drop, water coil air pressure drop. I need my solution method is leaving air temperature, solution target 80 degrees, altitude 0, entering air temp 5, wet bulb, match 55. Water temperature. Model is SDV, size, casing standard. Oil type is standard, my rows are referenced up here. Airflow is heating airflow. Actually, we want max pressure drop, so I'm gonna do design airflow.
There you go.
And I'm gonna click OK. And of course it didn't work. I'm missing. Something's down here. True, fluid type, water, 0. You're getting an error with the water.
You still have 45 seconds.
Oh, because this needs to be changed. Ah, I got it. Here. Okay. Now.
Looks like a lot of effort for 5 boxes, but if you had 500.
Well, yeah, once you get it set up.
So this should be the effort for the schedule for your office for the rest of your career.
Exactly.
As long as you're using single duct boxes, you build the schedule once. Or we'll build it for you.
Okay. I need to figure out what it's not liking. It's unrecognized text.
Something you typed in instead of picked.
Probably.
Clearly you can see how easy this is.
I got really good at it because I built like 4 or 5 schedules in 1 week and I got really good at it, and now I just need to play with it. But I'll answer your question 1 second. You can see here I've got 2 tabs at the bottom. I have one solving for leaving air and I've got one solving for fluid flow. So if depending on the project, you could just reference the schedule that you know is going to need what your solution method is going to be. Here, fluid flow is my target, so I can now change fluid flow and get the resulting performance that I need.
Yeah.
Yes.
My question, when you were adding that new function, does that automatically fill down then with all of the rows that are existing?
Yes, so because I have the function in this cell here, I just clicked and dragged it down and it then referenced everything it needed to. If I were to set it up properly, because you can see here, if you know Excel, you have to put the little dollar signs.
Right.
You don't want it to jump cells. So I set this one up properly, did all the dollar signs, and then yes, then you can click and drag and it'll work.
Yeah, it's pretty easy to pick VAV boxes when you've got 180-degree water. You can fall out of bed and kind of guess and you're pretty safe. But with, a lot more heat recovery chillers and lower water temperatures and condensing boilers, being able to design around 120 or 140 is really challenging for bigger boxes. You end up with these decisions about, well, using high capacity 12 fins per inch coils. Well, that's great, but now I don't like my leaving water temperature, and my condensing boiler doesn't like big temperature swings. So you go back and forth and back and forth. And it's just better for we're happy to pick a lot of boxes. That's not a big deal. But then the engineer says, can you solve everything the same but change the leaving water temperature? It's like, no, you have to solve everything at once. And you have to pick your criteria. So it definitely is an engineering challenge to get a lot of heat out of a coil when the water temperature is so low without killing the system.
Right. Yeah, so if we're working on a weird project with 120-degree entering water, we did a project in Seattle with 90-degree entering water. I wouldn't wish that upon anybody, but you can see here it is, really quickly I can see what do I need to do to actually make 120 achievable. All right. Yes.
So I've noticed that most schedules have an MBH, but not boil rows.
Mhm.
And I was taught that the MBH should be equal to or slightly above what the schedule says.
Mhm.
So if you have, let's say hypothetically, the MBH is calling for 15 and a 1-row coil is 10, but a 2-row coil is 25. I know that wouldn't be the case.
Uh-huh.
But what would you recommend there? Would you rather be 5 below what they're asking or 15 above? Or would you use an oversized coil there, or what's your recommendation on that?
Yeah, exactly. So I would also be checking leaving air temperature.
Okay.
You want to make sure both capacity and leaving air temperature, usually you want to be meeting or slightly exceeding on both of those. So I'd be checking both, but then yes, I wouldn't always jump from 1-row to 2-row. Now I might check either a high capacity coil or keep it at 1-row but go oversized casing. You have 3 or 4 different options to play with and look at. Maybe 2-row oversized gets you even closer, I don't know. But yes, jumping rows shouldn't just be the automatic, I'm always gonna increase a row.
Okay. And to help you out with your decimals there, it's right above X. Those 3 zeros. Get rid of the decimals.
Yeah, that's what I was doing, and for some reason it's not.
Oh, it's the other one, that one.
I swear to you, I was just doing that.
You were
It
doing
was not working.
You were doing the indent. That's okay.
Sure.
Oh, this is what happens in live demos, people. I promise I knew that was there. Okay. Any other questions on the Excel toolkit? Cool. I know Mauricio, I know you're online, and give me 30 seconds, I'll pass it to you, and then guys, I'm gonna come back to Revit after Mauricio. I just don't want him to be sitting online for too long. So my last note here, I did kind of point out that there's diffuser selections in here. 99% of people are not gonna be using this for actually building out diffuser schedules. What this tool is nice for is checking performance of like 1 or 2 very specific, maybe weird scenarios. It does, again, have a ton of different information, but it allows you with a single diffuser to set your sizes, check your, set your airflow, and then see what your velocity, what your throw, sound level, pressure drop is, etc. We'll go over throw and all that later, but you can get all of your performance in here as well for grills. Again, you're usually not scheduling this. This is not the process, I would say, for scheduling diffusers. But it's available, and if you have a weird scenario, it's kind of nice to check. You know, maybe you want to see if two diffusers, if they run into each other, what the throw will be, whatever.
You have like drum louvers and stuff in there too?
Are there drum louvers in here? That would be like a high capacity drum. It's kind of like a grill.
Yeah, maybe not.
There's a ton of stuff in here.
There it was.
Yeah, high capacity drum. There you go.
Wow.
I'd have to go in and change a whole bunch of these. I don't know enough about grills to make this actually work, but yes, it's there. Okay, so that's the Excel toolkit. Again, plug in from Microsoft, so loads up super quick and it'll just live on your computer. As long as you're on internet or on Wi-Fi, it will continue to pull in that performance. All right. I am going to come back to Revit, but for now, I'll go ahead and turn it over to Mauricio. Mauricio is our applications engineering manager for noise control, price noise control. So silencers, acoustic louvers, acoustic panels, it's kind of his bread and butter. He's going to jump in and just talk about selections for silencers quickly. Mauricio, are you there?
Hi, yeah, I am. Can you hear me okay? Can you see me?
Oh, yes.
Hi everyone. This is fun. I learned a bunch too. All right, so I'm just going to try to grab my screen here. Give me a second. And please let me know that you can see it. All right.
Not yet.
And it should be now. I haven't
Yeah.
used Zoom in months, so hopefully this goes well. All right, so thank you, Elizabeth.
Mauricio,
Yeah. Hi.
Mauricio, you've got 20 minutes.
All right, I have my timer. Go. Again, my name is Mauricio Salinas. I'm the application manager for noise control. And I hope you are ready for a software that I wouldn't qualify as boring. I think it's very exciting. It's pretty easy to use, and it can be used even when you're trying to see if your terminal units indeed meet those NC levels that are specified. In order to get the software, in case you don't have it, you could open priceindustries.com. You go to resources, go to software. You download all-in-one software for engineers, which I think you all already have. I think you all have it. Once you do that and open the software, what you're going to see is something like this. As Elizabeth mentioned, if you want to select terminal units, diffusers, fan blower coils, noise control products, or use one of our tools, which is the acoustic analysis tool, that's how you would access it. All right, so so far so good. You can hear me okay? See what I'm sharing?
Yes.
Okay, all right. So now if there are three ways to select silencers in the software, and I'm going to show you in the demo here. One is going to be by scheduled performance. One's going to be by design criteria, meaning you have a fan and then you have sound power levels and you want a quick selection of a silencer to get you a certain dBA level or DVC, whatever the weighting method specified by an acoustician, building owner, or your jurisdiction. And then for more expert users, you might be able to select by model or doing an acoustic analysis to specify the performance required or that performance that goes into a schedule. Typically, when you're selecting by performance, an acoustician already did an acoustic analysis, which means you have the minimum insertion loss required to get to an NC level in the space. You have airflow, you have models, you have sizes. So that's number one, right? You want to put all that information, and the way to do that in the software is you go to the noise control icon. And when you open that, the layout is a bit different than other products in all-in-one. You can add your tags easily. You could have your silencer type, so absorptive, most applications, schools, commercial, whenever you have a more stringent requirement where you have to keep the the air quality clean, you have a polymer film bagged option, which is going to prevent erosion of the media into the airstream. If you have dimensions on the schedule, you can do that. Now, this software actually talks back to you with information. If you don't know what our maximum minimum sizes are, when you scroll your mouse over any of the windows, it's going to tell you the minimum dimension standard, which is 6 inches, all the way to a silencer bank that's 480 inches wide. And same for the height, same for the length. Now you could allow for shorter results if you want to be more economical. You have your airflow requirements. You have, well, obviously this is going to have to be a bit more for 24 by 24. Now, the good thing about all-in-one too is that you could add system effects. So the forward flow is typically referred to as the supply or exhaust. That means that the sound is traveling in the same direction and airflow. Or you do a reverse flow, which means for a return application, sound is traveling opposite to airflow. That changes performance, so you have to pay attention to that. Now, typically, I would say if you don't have a lot of information, hopefully you do, you don't want to select a silencer that's over 1/3 of an inch just to be safe. And then you can add system effects for pressure drop. So what is the location of the silencer relative to the next element in the ductwork, right? So if you think about the test standard ASTM E477, you have 5 equivalent duct diameters from at the inlet from the silencer to the next duct element, and 10 equivalent duct diameters at the outlet. That is that perfect lab ideal condition. You typically don't have that. Right, so if this is really close on the vertical to the rooftop unit within 5 equivalent duct diameters, then your inlet condition for a forward flow on the supply is going to be fine. The outlet one, if you want to keep a straight silencer, then you probably have an elbow, right? Either with or without vanes. Now, if it's coming from the vertical, most likely you don't have a lot of room, right? So then you can play with that. Now, what the elbow is good for instead of a straight silencer, and I'm going to show you what that is if you were to select this, and let's say you have that performance required from an acoustician already, and this is the first type of selection that you could do. You already know the performance that you need, so that's kind of what we're doing here. Assuming that that's the case, a polymer film bag, because this is going to go into, let's say, a pre-operating room, so it's not as critical. You can have fiberglass. It is on the vertical. You have a good sealing in place, so you don't have to worry about breakout noise through the casing. If all of a sudden your silencer is right above a critical space, think conservation of energy. A lot of the sound is going to want to come out from the casing, radiated noise. So if that's the case, maybe beef up your casing. Now, once you have that, you click search, and it's gonna start searching for all the possibilities, all the different models that meet that performance. Now, the software is gonna talk to you. If you look at the information buttons, when you wanna understand the coloring, if you are in red, that means you're short in performance. The difference in performance to get there is greater than 3 decibels. In general, the industry allows you to be within 3 decibels short of performance because the human ear cannot perceive a 3 decibel change. That's why that is typically allowed. So anything that's a bit shorter on performance, but within 3 decibels is going to show as blue. So if you look at here on the 250 hertz, we need 10, but we have 7, so it shows blue. And then anything that's black is meeting performance. Right, so this is kind of, you can see you are short on all of them. This option actually has some blue and a lot of bolded black numbers, which means on all of those you're exceeding performance. Now, the only thing here is that your pressure drop is a bit bigger than the limit that you gave to your system, right? So in that specific case, you might wanna allow for more, but there is a quick and easy way to boost performance on the lower octave bands. The lower octave bands, the lower frequencies are the hardest to attenuate due to the size of their wavelength. So if you want to achieve a bit more points, you might want to try an extended casing silencer, which adds wings, so 6-inch wings to your unit. And if you look at that, at a 0.4 installed pressure drop, you are meeting most of the requirements that you need. Now, that's one way to boost performance for a silencer. There is another way that has less of an impact on pressure drop, which is making it longer. The longer the silencer, the better it's going to perform. And now you can start seeing that all your numbers are starting to become dark. Right, so in this specific case, if we add another few inches, you'll see that we get close to performance now. And you're gonna meet it under 1/3 of an inch installed that we were looking for. So that is one way to select silencers. And then it's gonna appear when you close that window, you're just gonna have your dimensions, you're gonna have your weight, you're gonna have your CFM, feet per minute, pressure drop installed, insertion loss, and also very importantly, generated noise. And that is a topic that causes confusion because you might think, hey, I'm taking 7 points out, but I'm adding 49. Well, that's not really the case. I'm going to show you that at the end. Sound is a logarithmic addition. It's not an arithmetic one. So when you think about the sound levels of a fan that are in the 80s, 90s, 70s, or even a fan power box, again, 60s, 50s, when you add 60 decibels to 49, you still have 60 decibels. So you are not adding sound. In general, the way to think about generated noise, just because we don't have a lot of time to go through several examples, is if the generated noise of a silencer is 10 decibels great difference, the difference between that and the sound power of the unit is 10 decibels or greater, you're not adding noise. Once those numbers are really close, generated noise to the numbers of the fan or a single duct valve, venturi valve, fan coil unit, if those numbers are close, you're probably adding noise to the system. That's why this piece of information is important to you. All right, so it appears that I only have 11 minutes left, so let's pick this up. There is another way, selection by design criteria. You might have sound power levels of a fan. This is an array of 4 fans pushing 50,000 CFM. They have a total external pressure drop that the fan can overcome of 1.5 inches. And you have the array of silencers for the outlet. We're going to look at the discharge, have that sound power level per octave band, and you want to know how quiet you can get it, right? So in this case, the way to read this is sound power in one number. They logarithmically added all these numbers, 96, 93, it's 92 dBA sound power. That's the amount of energy the unit is radiating. Now, the 81 that you see sound pressure, that is how that 92 decibels is heard by the human ear 5 feet away. And I know that because I'm reading this note on top that says that they are taking 12 decibels off to simulate 5 feet away. So that unit at 5 feet is at 81 decibels, exposing the human ear over 80 decibels for prolonged periods of time. It's gonna induce hearing loss, so you don't want that. You wanna bring those down. So in that specific case, if you have that specific scenario, you might wanna do a silencer that covers that entire area. You might wanna have a 1 to 2 feet duct extension and then do a silencer that's about 90 inches by 90 inches with 50,000 CFM. So if you do that, and I think I have, well, let's just do it quickly here. They wanted an elbow in this specific case. Any questions for now? Does it make sense? Am I going too fast?
Nope.
Maybe. All right. So discharge, and then you select by performance. In this case, is by design criteria, right? You can play with your leg lengths of your elbow. You might not have a lot of room on the vertical, right? You might want to have a different leg length. So in this case, because the width is 50, to make it an elbow, you need a little bit of distance to turn it. The minimum distance as a standard is 7 inches. So this leg in here, the smallest you can make it, if it's a 50-inch wide, is going to be 57. Now you don't have to think about it. If you scroll your mouse, it's going to tell you what's the minimum leg length you could do for that width of a silencer. And because you're fixing your center line length, it's going to automatically size the outlet leg of that elbow silencer. Every time you see a specification for an elbow, the length that they specify is the center line length. It's not the inlet outer leg plus the outlet outer leg dimensions added together is the center one. So have that in mind. And then in this specific case, let's say they want to bring it below 70 dBA. And you have the sound power levels that we were talking about. So let's just quickly do it. 90, 87, 86, 83, 81. Okay, that's how fast you can move. That's not pre-recorded. That's how fast I type. And when you go and look that, you can see that you could add flanges if you want to attach to the fan, of course, because it is bigger than 48 inches. Sheet metal that you can get from most manufacturers is 48 by 48. Now you're going to get those dimensions in multiple components. That's when it doesn't let you do flanges that are attached. Then if you want that to be a low leakage, because it's going to be situated outside and filling every single potential gap, because we're using a snap lock to build the silencer, you do mastic fill seams. If you want to protect them so that they don't get banged up in shipping, you could add plastic cover ends. And then you're going to go and tell the software, hey, find me a silencer that meets that. And when you look at that already, it's telling you that if you size any of these silencers here, you're meeting your design goals that you wanted to meet by bringing it below 70 dBA. Now, one thing I didn't tell the software is that this thing has 50,000 CFM going through. Now, what happens when you do that? The software right away tells you, consider using fiberglass cloth liner at higher velocities to avoid media erosion. So right away, it's going to let you know, hey, you need to protect that because it's a lot of air you're trying to put through the silencer. Now, this is phase velocity on based on 50 by 50, right? But when you are putting air through a silencer, you are constricting the air by at least 50%. Right, so then the speed going inside the silencer is going to be much higher than that. That's why you're trying to add a fiberglass cloth bag in it. Now, if you want to keep it at 60 dBA at 0.5 inches of pressure drop, then that's what you would be adding for that specific scenario. So in this specific scenario, they were doing 9 arrays into a generator room, and then they were sucking all the air through the top. And it was 9 inline generators. That elbow that you see here is the one that they sized times 9 to try to keep sound levels at bay. Now we did the same to size the silencers at the inlet side of that fan, facing residential buildings on the other side. And we added rain hoods. We customized everything that we needed. So that's how you use that. And then the last way to use this, well, one of the last ways is to know the model. You already know what you need. You know that R is rectangular, ER is an elbow rectangular, packless silencers. And what you do now in the software for that scenario is you go and just type exactly what you need based on the model. And if you know specifically, I know Price models by memory because they are the best manufacturer for silencers. I can trust them because they have the latest and most accurate performance. So I'm gonna always use them. So when you do that, let's say select the silencer and you know that you want a 1A with 1,000 feet per minute. And then you know kind of what to expect. Sharp in, let's say you have a fan, and the duct is doubling, so transitioning, and that's the performance of a packless elbow. So as you could tell, the packless is going to perform less than something with media, right? So have that in mind. If you're dealing with a hospital, make sure that you use the software to get the accurate data. If you may grab the catalog and think, oh, I like this silencer, but don't realize that it's an absorptive silencer, then that's different. So all our models are here. They tell you exactly what they mean. And that's how you would select them. Now I have 4 minutes to talk about acoustic analysis. Another way that you could use the software for is using our acoustic analysis tool here through all-in-one. So let me just go here to acoustic analysis. And what you can use this for is to really indeed check on real life conditions if your size 7 SDV 103 that Elizabeth was showing you before is indeed going to meet the NC level on their AHRI 880. Now, when you're rating terminal units using AHRI 880, it takes a lot of assumptions. It assumes 5 feet of line duct. It assumes it has a junction with certain amount of branches. Then you have a bunch of insulated straight duct, and then you have a 400 square feet or 20 by 20 by 10 foot high room with a distance to the ear of 5 feet from the air outlet with 2 diffusers or maybe more. So that is kind of a bunch of assumptions that you might look at and it'll be like, oh, I'm gonna be at NC 51. But that is only the rating that you see in the catalog for terminal units. It's only there so that you can compare apples to apples with other manufacturers. If you really want to see how loud the space is going to be, you got to look at the right application. If this is going into a pre-operating room, well, it probably doesn't have line duct, right? So all of a sudden, you don't have that. And you probably don't have any flex duct either. So then you're starting to get a little bit louder. Then the space is a pre-operating room, so it's not average anymore. It's medium live, right? And you're gonna have people standing by it. And if the diffuser is really close to a wall on the ceiling, then you have 2 reflective surfaces. So all of a sudden you have your NC 50 rating for HRI 80, but in reality it's in NC 59. Does that make sense? So far, so good. Now, the good thing is if you have that terminal unit that has to create noise because you're trying to push so much air through it, then you could add a silencer and easily fix the problem. And perhaps a film line back because you have a filter downstream. And this is a silencer for SDV 103. You want to make it extended casing because if you're an expert like I was and I am, you know that the lower bands are driving that sound. You're going to have some system effects. And because this is probably really close to the occupied space, I'm going to beef up the casing. I'm going to try to look for a silencer that meets that. So in this specific case, this gets me under NC 50, that space. And when you go and look at that, you're at NC 45. In the space. All right, loud and clear. And this Bear Online circular, sorry, this is a circular duct, so you're at NC 45. And the cool thing is that now, if you did this with every terminal unit, with every rooftop unit, with 1 click of a button, you can create a report with all your assumptions. It literally takes seconds to load up. Right away, it's going to give you a schedule that you could put in your drawing as BOD with all the information to get you to that NC level, NC 45, with maximum generated noise values, right? You need this to be the max because I could add to the overall level. This is the minimum insertion loss, the sound you're taking out of the single duct valve. This is your installed pressure drop. These are your dimensions. And this is the report that will back up your selections. And that's how easy it is to use a very exciting software that's not boring at all.
Yes, question. There is one, Mauricio, hang on.
So I was picking a silencer and are there any limitations on the dimension requirements when you pick an extended casing?
Yes, there are some, and the software typically kind of guides you. For example, if you're doing an extended casing, your minimum length has to be 36 inches. You cannot do a 24 inch. Okay. So if you want to try to look, it won't let you. So yeah,
no, I did not get an error, but I got a question mark on the pricing. I did not get any pricing, but when I clicked the standard casing, I got a pricing though.
Okay, well, if you're a rep, you should get pricing. If you are not a rep, you should not get pricing.
He is a rep. He is a rep. So you got a valid selection, it just didn't price.
Yeah.
Yeah, so anything that's 10 gauge or continuously welded, anything that's stainless steel or aluminum, because
it was stainless steel.
Yeah, so if it's stainless steel, most likely it won't give you pricing. If it's a light gauge stainless, it will. If it's heavier gauge, it won't, because that's gonna fall under a special. So that's how you know when something is a special, if it doesn't give you pricing.
Okay. Very good.
Was that for?
Any other questions in the room or
We
online?
went around it, me and Mike.
Silencers in this super awesome software.
Thank you, Elizabeth.
My last question.
Yes.
So if I don't meet the insertion loss for 4,000 hertz or 8,000 hertz, does it still matter? Because I don't think we can hear 4,000 or 8,000 hertz.
Well, you can hear it if it's at a certain level. And in fact, these three frequencies are very annoying to the human ear compared to the lower frequencies, because that's why you like cranking the bass in your music.
Yeah.
It doesn't bug you, right? So the ways to get better performance for those bands is typically closing the internals of the silencer, which means you would have to play with the letters. So A is about 60% free area, and as you go up, you're closing the gap. So for example, this silencer here has an F, right? So if I want to get more performance, I would have to make it a G gap. And you can see that it gave me more performance on 1 point on the 4,000 hertz only, because it's only 24 inches long. And then it gave me 2 more points on the 8,000 hertz. And it actually gave me 10 more points on the 2,000 hertz. So if you want to start gaining more performance after that, you'll see that it really increases your pressure drop. You see that?
Yeah. Just a little.
Closing the gap. So the best way to do that is use a high-speed silencer, which tapers your the internals, which allows you to gain static, allows you to do some static regain. And remember, the limit is 36, and make it longer. Making the silencer longer will allow you to get that performance that you need. And I think here I just have to play around with the dimensions to make it happen. And it's going to start giving you more. So it's 2 ways. Selecting the right model, increasing the length is going to give you more performance, or increasing your air gap. It's going to start giving you more and more. Now, this is an RA checks, but you could also do an RM, right? And in that specific way, you start gaining more points as you close the air gap. So it is not as easy to just think what you could get. If you have a set amount of performance you need to meet, I would put it in here so that the software searches for you every time. And then you might be making your silencer longer, or make it extremely long and click allow for shorter results and get a silencer that gets you the 20 points off with those dimensions at the 4,000 hertz. So in that case, it's going to think a little bit longer, but it's going to target that 4,000 hertz, and automatically it's going to think of all the different options so that you don't have to play with the length, and give you the optimal solution so that you are not increasing a foot every time you try to select a silencer. The reason it's taking more than a minute is because it was looking at all the different options. So in this case, if you want 20 points off on the 4,000 hertz, you need an 84-inch long silencer.
Okay.
And yeah, that's how you do it. You go to the Home tab, you add the new silencer that we have there, and you have everything that you need in front of you. All right. Any more questions?
Thumbs up. Any other questions?
I know I missed the whole thing, but I just wanted to, sorry, one thing I want, hey Mauricio.
Hi, Tom.
Hey. Oh. Hey. I just want, I don't think we went over, I'm sure we didn't go over pricing. Straight silencers are super cheap. Anytime you're putting up a rooftop unit, budgeting a job, just get a price for a silencer. It seems like the labor to have a silencer is more expensive than, like, the engineering labor to create a silencer is more expensive than the silencer itself, but silencers are super cheap. Even if you do fancy extended casing or line or whatever, and it can have a huge impact. Get rid of the duct liner and all that kind of stuff. Just put a 3-foot or 5-foot silencer, leave space. It's going to make your jobs better. And you're replacing some sheet metal anyways. So it's not like the net cost is next to nothing. So I highly recommend it. Price is great to work with. Don't try to sell you a bunch of nonsensical, heavy gauge bells and whistles, elbow silencers. Just will make it right for the job. So that's my 2 cents worth.
Yeah, no, thanks, Tom. I thought maybe we had some engineers in the audience. That's what I was using the engineering edition.
Yes, yeah, you do, Mauricio.
Okay, so, but yeah, and the way the software searches for things, to Tom's point, is it's always looking for the cheapest option first. But the moment you give it requirements for pressure drop, insertion loss, then that's gonna override pricing and it's gonna make that priority. But yeah, silencer, a 3-foot long silencer, it's gonna outperform 10 to 15 feet of line duct. So it's always gonna be cheaper and it's gonna last longer because the insulation is not gonna come off either. But yeah, well, thank you all for your time. If there is no more questions, I can hand it back to you, Elizabeth.
Thanks, Mauricio. Good to see you.
Yeah, good to see you too. I can't find the button to stop sharing in my screen, so
Up to the top.
you might have to kick me out. The view that I have is very weird. Oh, there you go. I have it. Thank you. All right. Have a nice day, everyone. Bye.
Mauricio, thank you.
Bye, thank you.
All right, why don't we take another, we'll take a break till 11:10 and then put a bow on this.
Perfect.
All right, sounds good. Take some joy out of that. Oh, no.
Yes, thank you. I mentioned to forget this. There you go. Thanks for running. Yeah. All right. I just need this little toolbar to disappear so that I can change my tab.
You can just click it and drag it. We can't see it, but you can.
Okay, that'll work for a second. Okay. So I'm gonna pick back up on the software. I will get through the Revit in 5-10 minutes and then we'll jump into GRD. And that might bring us to the end.
Excuse me.
Bless you. We already looked at Excel. The last two toolkits are plugins for Revit, again, for our engineering community. The first plugin is the Price Industries plugin for Revit. Bar here. So at the top of my Revit, I have two toolbars. I've got two additional toolbars now at the top of my Revit here. So the first one is the Price Industries plugin. There's really only two main features of the Price plugin. The first is this product families library. Previously, if an engineer wanted to use any of our Revit families, they'd have to go to our website, download the family and upload it into Revit. Now you have the entire library or catalog of product family models in Revit. So if I'm looking for a single duct, I know the SDB, I can just click search. It'll give me that model. I can add it straight into my schedule. No more downloading from the website. If I don't know exactly the model that I'm looking for, but maybe I know I need a grill for a gymnasium application, I can filter down by grills and then look at some of the different filters here. So mounting type, frames, application. I'm going to search gym grill here, and it'll give me a couple of different options for typical gym grills. So you don't need to remember all the model codes, although you should, because as Mauricio said, we're the best ever. So you can simply select the family and add it to your Revit model. Now, one other feature here, there is a favorite star. If it's a model that you use all the time, square black diffuser, single duct, you can add that to your favorites list, and then you will have access to those models very quickly to your favorites list. So you don't have to navigate through the library every time. So first big tool of the Price plugin is the families library. And if we make any changes to any models, dimensions, etc., that'll automatically get updated. Second feature here is the competitor cross-reference. Maybe you're cross-referencing a schedule, have an old model and need to find what a new modern day manufacturer would be. I can search the model code, so I know the tightest single duct is a DESV. I can search that. And it'll show me, it'll give me the Revit family for the price version, but I also now have hyperlinks to get to web pages. So if I need more information, submittals, whatever, I can click the hyperlinks and they will bring me to searches of that product. Again, if I don't know model codes, because that would be thousands to remember, I can filter down by manufacturer and then product type. Any product you could think of, manufacturer is probably in this list. One other thing I forgot to mention about the product families, every product that Price manufactures is in here. So it's not limited to just GRDs. We've got chilled beams, fan and blower coils, terminal units, underfloor, VAV diffusers, every product you can think of is going to be in this list. So again, for the Price plugin, competitor cross-reference and family library. Those are the two features. Now the actual fun and exciting one is the plugin for the Ripple HVAC plugin for Revit. Ripple is an independent software company that Price partnered with. So Ripple actually built this software, but the agreement is that Price product is inside of the software. What Ripple is, it's an auto sizing and auto placement tool for grills, registers, and diffusers. So in this Revit model here, this is a school building. This is one floor of a school. So here in just a second, I'm gonna highlight a couple of rooms, go to my Ripple tool, and without doing anything, I'm just gonna click place air terminals. Within a couple of seconds, in those 3 spaces I selected, we are going to see all of the diffusers pop in. So we've got all of our supply diffusers as well as exhaust and return diffusers. In this room here, we have a ceiling grid. So it selected a 2x2 diffuser and snapped it to the grid. In this space down here, we don't have a ceiling grid. So it went with a round cone diffuser mounted in an open ceiling application. Now, what is it the tool actually requiring to make this happen? It requires 2 things. In your Revit model, all of the rooms need to be defined as spaces. So this room right here is actually denoted as a space in Revit. The second requirement is airflows. It requires your supply, return, and or exhaust airflow to be established for each space. So then the tool can take that space, its requirements, and choose the number of diffusers and place them. Now, how is it sizing? You do have some control over the parameters there. So back in my little pop-out window from the Ripple plugin, I can set the parameters on how it's going to size all of my diffusers. For example, maybe company standard is that we don't size 6-inch necks above 180 CFM. I can set that, and now the program will only choose 6-inch necks at 180 CFM or less. Maybe sound sensitive project, we want to target 22 NC for all of the diffusers. I can set that as a requirement and it will, set the resulting airflows. So you have the ability to set up the parameters for the placement. And then you can also choose the model type. So square plaque, square cone, or perf. If we have a ceiling, if there's no ceiling, it's going to default to the round cone because that's all that's in there right now. And we can set the height of where that diffuser will land in the space. So you can set all these predefined parameters and then the selection tool will run based off of those. I'll finish this up by clearing this out and then kind of running the whole school building so we can see how long it takes. Maybe if someone could pull out a timer and we'll time how long the auto placement takes. Who's gonna time it? Tom, you got me?
Sure.
I've heard from engineers that something like this for a school of this size, you ready?
Go.
Could take a couple of days. This is a 3-level school building. So could take a couple of days to actually size and place everything in the building, at least a number of hours. My guess is that we'll be at about 45 seconds, but Tom will tell us exactly how long it'll take. Once all of the diffusers do place in the building, we have it will build a smart schedule out for us. So I can show you, I'll pull up the schedule and show you what it's building out. It's pulling every single diffuser into the schedule with its performance, airflows, et cetera. I passed 45 seconds yet?
45.
So close. All right, so less than a minute. We have, I believe, 128 diffusers out placed. Okay. Now if I zoom into some of these rooms, you can see it's for the supply diffusers, just trying to pick the best location, usually in the center of the room, either right in the middle or, staggered pretty normally throughout the space. It's always going to try to put the return in the corner of the room. Now for a square room like this, it does pretty well. We've got a square plaque in each corner there. But you might look at some of these other spaces and think, what the hell is it doing? Why is it putting a diffuser in that little alcove? That may or may not be how you design it. Believe it or not, the goal of the tool is not to get rid of your job as an engineer. We're trying to help expedite the process and get you about 70–80% of the way there. The way this is laid out, I would not say is the end and you can send it out for plans. It will need some adjustments, like you'll probably need to grab that diffuser, maybe move it out to the middle of the room, make it more intuitive. We probably don't want these two returns next to each other, so maybe we put the return in there. You have to use your engineering brain still and make some adjustments, but it will get you a majority of the way there. It's pulling out a lot of the copy and paste of diffuser selection. So this library here, looks pretty good. We're pretty staggered throughout the space. Again, get you close, but it's not perfect. Pulled it up there a second ago. Here's the schedule that it's going to build out. So this is an every instance schedule. Every single diffuser that places, it will list the room that it's in, as well as the diffuser size, the model, airflows, etc. And then there's a more condensed print version that an engineer might actually put on a set of plans. This is filtered down pretty far right now, so it's just giving us total count of every diffuser. You could change that filter to filter just by maybe model or size and quantity, etc. All right, I ran through that pretty quickly. Are there any questions on the Revit plugins?
It's a little daunting, actually. It's not, it just seems too easy.
Yeah, most of the feedback I've gotten from engineers is they're very hesitant. I don't know if I want to trust that. But it would take some playing around, getting comfortable with. And we're continuing to build it out, make improvements. Currently, they're about to release another tool that does auto zoning and auto sizing for VABs. So it'll take your building, zone each space, and add a VAB for that specific zone. That should be out in the next month or two. I've seen it demoed once, but it's not live yet. And then they'll come back to this air.
Since all you engineers are going to be looking for jobs, there's always openings here at Airport.
I'm not trying to take your job, just save you time.
And I, for one, welcome our new overlord.
So again, your two plugins there, the Price Industries plugin and the Ripple HVAC plugin. The QR code on your flyer can get you to download both. These plugins are through Autodesk. So back on that website here, if I click on the Revit plugins and download, it brings you straight to the Autodesk store. That'll just add the plugin straight to your Revit. On this landing page, there are a ton of how-to videos. These are more like 15–30 second videos to be very specific things within the tools. The videos on the front here are your 15–20 minutes of like longer form videos for the whole tool. So that landing page can be helpful.
Elizabeth, you know how we'll do like an acoustical layout, lane service for acoustics? Are you
Yep.
guys, do you think that that'll be something you will just lay out all your diffusers for you at some point?
I hope not. Probably not.
I mean, because every engineer conceivably could learn how to use the acoustics program, but very few actually do.
Yeah. And I would say not every job needs an acoustic analysis, but every job needs diffusers laid out. So
Right,
that's,
fair.
yeah. Time wise, I don't think we can take that. We would
Yeah,
be
no.
doing engineer's job. Anything else?
Interesting.
I could spend an hour on these tools and go into all the features and functions. I don't want to do that right now. If there's anybody interested or anybody online who wants more and wants to do a follow-up webinar, maybe with your firm, let us know. We'd be happy to. I'm gonna go ahead and stop sharing my screen and we can switch over to our last presentation. Presentation. The blue one there. Okay. Then the lights. There's a couple of videos in here that I can see. All right, we'll close off here with general
Close
overhead.
off here, Elizabeth, this is a G-rated audience.
I don't even get that reference.
Just said close off here.
Oh, wow. Okay. We'll finish out the presentation here. Goodness. With overhead mix systems and girls registers and diffusers. So even more commodity than our terminal units. We'll start super basic again, air distribution systems. This probably should have been the very first slide we ever even had up. But everything we've been talking about today, all the products fit into your standard overhead mixing system. So I'll start over here in your overhead mixing system. Typically, we're gonna have supply air coming from overhead, either returns low in the space or back on the ceiling. The whole goal of a mixed system is to get the supply air to mix in the space. So we're discharging out of the diffuser, training. Thank you. Entraining the room air and getting the space to mix. I've got a couple of smoke videos where we'll really see that in action. The opposite or another type of system would be a stratified system. In a stratified system, air is moving in one direction through the space and there is zero mixing. So if you ever heard of displacement ventilation, this is that type of system. We're going to deliver air usually at the ground level. Our return is at the ceiling, air is gonna travel up through the space and out the exhaust. There is no mixing. Pluses and minuses to both systems. I'm not gonna spend too much time on that today. We're just gonna look at,
We have a displacement class later in the year.
and everybody should attend, because displacement systems are the future per Tom Lee. In a mixed system or just in any space in general, when we're designing, we are designing only for the occupied zone. The occupied zone is 6 feet off the floor, 3 feet from any wall, or 3 feet from an exterior wall, 1 foot from an interior wall. Anybody who's over 6 feet tall, we're not conditioning their head. We're only concerned with 6 feet off the ground. Smoke video of a overhead mixing system. So here, this is our flow visualization room at the Bryce Technical Center. So we have that lovely Falcons diffuser in the middle of the space there. We are sending airflow out. I can't read what that says. It looks at about 250 CFM out of our square plaque diffuser. The first step in your mixing system is that we're going to deliver air to high velocity across the ceiling. Anywhere up to 1,000 feet per minute, it's going to travel along the ceiling. The next step, as that air slows down, it's going to start dropping into the space. It's either going to travel down the walls, or it'll lose contact with the ceiling and just start dropping into the space. This is when it starts to enter the occupied zone. So again, 6 feet off the ground. At this point, ideally, our airflow is at a lower velocity, not super high coming out of the diffuser. We want it down to about 50 feet per minute by the time we start meeting the occupied zone. You will see some of this smoke now is moving pretty slow, and you might start seeing that circular pattern. So the air is going to start rising back up to the ceiling as it warms up, and we will start to see a mixing in the occupied zone. Here you can really see that well. All of the smoke is slowly kind of moving throughout the space. There are returns in the corners of this room, so you should see the air kind of start to make its way towards the returns in the ceiling. This is what a mixed system looks like. That means that any contaminants coming from me are getting mixed into the space with Tom's contaminants, and everybody's kind of breathing the same air. Sounds lovely, right?
Tom's contaminants.
Okay, that's a mixed system. Jump into GRD specifically in some of the terminology. So GRD stands for grill, register, and diffuser. These are your pretty much 3 different types of air outlets. The first one here being a grill. Your grill is your simplest. It's really just a hole cover, essentially. Very little variability in the discharge of a grill. Usually you're only discharging air in 1 or 2 planes. But very versatile as far as sizing goes. A register, I would say less common than a grill, but is a grill with a damper on the back. Damper is typically only used for a little bit of airflow balancing at the grill, but that's what makes a register is that damper. Finally, a diffuser. Diffuser is usually ceiling mounted and has a little bit more control over the direction of airflow. So we can be a little bit more strategic in where we're sending air in a diffuser versus a grill. When you're looking at catalog and performance, some words that you'll typically see, throw is the first one. So when you look at a catalog here, you'll always see throw in a string of 3 numbers here. Can anybody tell me what those 3 numbers are?
Velocities.
Velocities, what are those velocities? Well, okay, wait, the numbers are not velocities.
Through distances.
They are throw distances
At different velocities.
at different velocities. Beautiful. What are those velocities? That was a team effort. Who said distances?
That's
Okay.
50, 100, and 150.
Justin, put that in the chat.
Nice job, Justin.
All right.
Is that right? Remind me to send Justin some swag.
We're writing it down up here.
Oh, great.
Yes, so 50 is gonna be your 3rd number.
Gold star.
You said 100 and 150?
That is what I said.
That's what I said.
What does the chat say?
Should be 50.
5100, 150.
These animations are just stellar.
150, 150, perfect. So your throw is the distance air will travel out of the air outlet. And usually we're cataloging at these specific velocities. We're looking at what distance does our air achieve 150 feet per minute, 150 feet per minute. If you remember from our mixed air video, we are always trying to target 50 feet per minute in the occupied zone. That is our goal. So that is throw. We'll talk more about throw kind of towards the end, but again, just terminology here. Sound and NC is another very common catalog or scheduled piece of information. We obviously just talked about sound with Mauricio, but NC as far as diffusers, this is your sound level right at that one air outlet, but it is assuming a ton of things. ASHRAE gives this really nice chart with kind of recommended NC levels for each different type of space, but the what this NC doesn't account for is different types of spaces. So the NC number that you'll see in a catalog is assuming that there's carpet in the space, that there's line duct upstream of the diffuser, assuming there's a certain amount of absorption in the space. It's assuming a lot of things that might not be true of all spaces. So Mauricio kind of said this, but NC is really good at, comparing apples to apples. So you could take a Price Titus Naylor metal air diffuser and compare all of them per sound, but it's not 100% indicative of what it's going to sound like in the space. Yeah, that's all I'll say there. Grills and registers. All right, so now we're gonna actually get into some of the selection and performance, why we're actually all here. So we'll start with grills. The key takeaway for grills and kind of what we're gonna look at here is pressure drop in sound when we increase size. So we're gonna compare these two different grills here. We're pushing the same airflow. We've got 550 CFM through two different grills. One is 12 by 6 and one is 24 by 12, so double the size. When we keep airflow the same, but double the size of the grill.
It's not exactly double.
Quadruple.
Yes, yeah, because it's a square dimension. You're doubling each length. Thank you. Our velocity is going to decrease substantially. You're moving the same amount of airflow through a larger opening, so our air will move slower. We're also seeing a reduction in pressures across the board. Your total pressure, velocity, and static pressure are all reduced because we have less resistance to the airflow. And then our sound is also going to be reduced. So we're dropping from 32 NC down to below 15. Substantial reduction in sound with less resistance. But then our throw is almost the exact same. So we're getting a lot of benefits from a larger face with negligible impact to the throw distance. That is because throw is completely dependent on the mass of air that's coming out of that outlet. It doesn't matter how big the outlet is, it's just that mass or that volume of air. It's going to travel about the same distance regardless of the size of that outlet. So the larger the grill, the better. Of course, we can't start putting 5-foot grills on everything, but something to consider in your selection. Now we're looking at actual size of grills. The size that you would be selecting or scheduling, usually you're looking at a nominal size. I need to cover this opening. This is the size grill I need. The actual air outlet is always going to be a smaller dimension than the opening that we're covering. That's your core. The core is what our air is actually coming out of. And then within that core, you're probably going to have some reduction of free area. So even though our core is X size, there could be blades or dampers or something in that airstream that is actually reducing the air outlet to a much smaller free area. So we start with a grill as big as the nominal size, and we're actually down to this small amount of free area that air can actually pass through. What does that do for our performance? So free area, again, is our non-obstructed path for air to come out of. If we start with something like an egg crate, this is a pretty large and open grill. We've got 90% free area, so we're only obstructing 10% of the full nominal size. If we compare that to a louvered grill, you're down at 78% free area. But let's look at some of the performance metrics. Our pressure is going up, so we can see our static pressure is up 1/10 of an inch. And so is our total pressure. NC is also up 9 NC. So by reducing, what is that, 12% free area, we're adding a good bit of sound and pressure drop.
Yeah, why is the velocity lower?
Smaller opening should go faster, right?
Correct. Yeah, you're pinching off the airflow, making the air travel faster through it. The same volume. Because our volume stays the same, but with a smaller opening, it's gonna go faster.
Yeah, the louvered one should be a higher velocity then, shouldn't it?
Oh, wait a minute. You're right. I don't know the answer to that. What's this one? That one's the same velocity.
I think so.
So what it may be is actual core velocity. So the core is larger on the louvered than on the egg crate. Is that possible? Does that make sense? So it's not actually calculating your free air velocity, it's your core
It's
velocity.
your core velocity. Yeah, potentially.
That would make sense that
Yeah,
you
because you would have to have the air measurement upstream in that port. I'll check on that.
Isn't it the profile of the egg crate versus the louvered? So egg crate has, blockages, if you will, veins in both directions, whereas louvered will only have them in the one. So your velocity profile should be a little more or a little less turbulent probably in the louvered one. So maybe that's why velocity goes down.
Well, velocity should just be flow versus area. But it's not that important. Let's move on.
Some exciting grill and register debate here. Ladies and gentlemen, don't miss the next class.
I mean, I was wondering.
Oh, actually, if you look at what free area,
We read the title.
sorry, it's still different than, all right, we'll come back to that.
I'll send a message to the actual grill expert, because that is not me, and then we'll get the answer before lunch is over. Okay, so we looked at the small reduction in free area. Now we're all the way down at 51%, and we can see our static pressure that's 3 times. And then our sound is up again, 12 NC. So reduction in free area, increase in pressure drop, increase in sound. Diffusers. When we're looking at cataloged diffuser performance, we're seeing some of the same numbers, and we see sound, we see our throw dimensions. Diffusers are gonna have a couple more variables in there. Your neck size can be variable. So even though you'll always have maybe a 2x2 diffuser, your neck size could change from 6 inch all the way up to 12 inch. And then catalog performance for different neck velocities. Usually, again, we're staying below 2,000 feet per minute. But we can see what all the different neck velocities are and the corresponding sound and throw. Sizing for sound and throw is usually more important than sizing for a specific neck velocity. Pattern out.
If we just go back to the previous slide, I do notice many engineers selecting their neck sizes too large, which for design conditions, like I see a lot of 8-inch diffusers at 200 CFM, for example, which works great at 200 CFM, but what happens when we turn down and turn the heat on is we get absolutely no mixing. So you're getting 7 feet. Or maybe it's 300 CFM, you're getting 9 feet. So let's cut the airflow in half. We're not even getting to the wall. And then let's add some buoyancy. So it's not a great habit that we're oversizing diffusers. And so the net effect is, gee, it's fine in summer, awfully cold in here in winter.
Or you'll find like hot pockets throughout your space. Because that air is just gonna be dumping in one location, it's not.
Pollution.
The airflow pattern of diffusers. So even though we look at this, it's a square diffuser, and we would think we might get a square airflow pattern. We will have a radial airflow pattern, and that is because we have a 360-degree opening at the neck before those cones. Same thing with the plaque. Same thing with the round cone. The inside of the rectangular ones look very similar to the round cone. So you're still getting 360-degree release out of the diffuser face. It's just what we visibly see is a square. The square plaques and square cones are the most common diffuser and the best performing for a couple of reasons. You get really nice 360-degree airflow pattern out of them. Usually have pretty short throw distances, so we're not as concerned with drafts with this type of diffuser. Less impact by poor inlet conditions. So if we've got tight elbows, maybe some flex duct on the inlets, they're a little bit more resilient to that. And then they are also the best for turn down, as Tom was mentioning. So we can demonstrate this in the FlowViz room, but if you pump 500 CFM through one and then turn it down to 100 CFM, you'll get the exact same airflow pattern. It still will hug the ceiling a little bit before it starts dropping into the space. Not as much the case on a perf diffuser. I think I have an example of. Here's a smoke video of the square plaque diffuser. You can see that 360-degree release. And pretty quickly, we're going to start slowing down to our 50 feet per minute there at the edges. Other types of ceiling diffusers, directional diffusers. So this is a modular louvered face in a 4-way pattern. Core diffuser, so it'd be a removable core diffuser, again in a 4-way pattern. I had just mentioned perf diffuser. So you can kind of see behind the perf, there's some directional blades. With the perf diffuser, you get a little bit of direction. And I sort of mentioned the perf is really bad at turn down. Because of that perf screen over the face, as soon as you lower your airflow to a much lower velocity, 170, 70 or 100 CFM, that airflow doesn't go anywhere but straight down. The perf kind of stops any direction to it and dumps it right into the space. If you ever go into a Chick-fil-A, almost every Chick-fil-A has perf diffusers, and they're the cheapest but probably the worst performing diffuser. We'll just say that. The benefit of the directional diffusers is that they have longer throw lengths. So we're not discharging at 360 degrees. We're isolated now to 1, 2, 3, or 4 directions. So we can get longer throw out of a lower number of discharges. So many animations. 1, 2, 3, 4-way. This would be nice if we put it up against a wall. We can get 3-way. This is nice for in a corner if you need to go out 2 directions. 1-way, maybe in the middle of a wall, pointed straight out into the middle of the space. Oh, nice smoke video. There we go. Smoke video of a directional diffuser. So you're definitely getting more of that cross pattern, not a 360-degree release out of that face. And moving over to slot diffusers. Slot diffusers are definitely more of the architect's diffuser of choice nowadays. They're really easy to hide in architectural features. Yes,
We go back to the directional diffusers.
We can.
Jonathan Olson asked, is there a downside to using SMD diffusers instead of SCD diffusers? Oh, Tom's typing an answer.
No, I'm not. I was just opening it up.
Oh, okay.
Let's let the pro
SMD,
answer.
SMDs versus SCDs.
is there a benefit to SMD, to a modular diffuser over a
Is there a
phone?
downside to SMDs over SCDs?
Not necessarily a downside, if, as long as you're designing for throw properly. Because out of the SMD, you are gonna get a much longer throw. So you would want to, avoid putting them too close together and creating drafts. Checking to see how far the throw is gonna travel down the wall. The only downside is that it might take a little bit more kind of review of the performance to make sure that we're still designing for a comfortable space because of the longer throw pattern,
They're expensive.
and they're expensive. There you go. You guys are wrong. All right,
Jonathan followed up with, do SMD diffusers perform better at a low airflow?
they perform better than perfs, yes. Similar to your radial diffusers, not as good, but still a good option at low flows. Everything's better than perf.
I think he's looking just as a reference, but I mean, it's just a matter of sorting up catalog data and seeing which works better.
Yes.
I mean, seems like 90% of the stuff we're looking at is plaque, right?
Yeah.
Estimating team. Squares, cone or plaque,
CD,
yeah.
Yeah, the plaque and the cone are our two highest volume movers for sure. That's definitely the direction of the industry. Plaque is way more common than, not way more, is more common than cone now, just a little bit more architecturally pleasing. But they are the two, least expensive, best performing, overall good economical features. All right, slot diffusers. So your slot diffuser on the room side, you're only gonna see, a nice, usually continuous slot in the ceiling. Could have a frame on it, could just be a skinny opening in the ceiling that nobody even notices. High-end retail spaces love to use slot diffusers. Numerous different airflow patterns out of the slot diffusers. So this image or this graphic here shows a horizontal throw pattern. But we can go horizontal either direction or straight down vertical out of the slot. So it just depends on, maybe we're washing a window, or maybe we're designing for normal overhead, trying to shoot across the ceiling, different configurations for both options. And then there are slot diffusers with variable control patterns in there. So this slot diffuser image here is a 2 slot. If we put that against a wall, we could have maybe one slot washing the window and running down the wall, and the other slot is directed out towards or across the ceiling. So you've got some variability there when you have more than one slot. And you have the variable ice tongs.
We know that the contractors all set these pattern controllers, job specific every time.
Yes, they're perfect.
They're perfect.
Now this is a fun one. If we are designing a space with slot diffusers down the center of the room, they're going to discharge across the ceiling like this. What happens when we put our returns on the perimeter? It's a good design, a bad design, and why?
Oh, she's getting out the tickets. Who
Come
can
on,
answer?
who knows?
You get a ticket for a bad answer?
Yeah. Give your best shot.
Walk, walk.
Somebody's got something. Tell me it's good or bad.
Looks great.
Yes.
Is it bad because it goes straight from the supply to the exhaust without flowing into the air?
That was the answer.
Oh, man.
All
Good job,
right.
Zach. You get two for that.
Sweet.
Wow.
And
Great.
we call that short circuiting. So yes, this configuration here, I guess I gotta, should have put some more animations, maybe that would have given you guys the answer. This configuration here is what we call short circuiting. That is, you travel right across the ceiling and get sucked up into the return, not allowing for any mixing in the space. So ideally, I guess, let me ask you guys, where should we put the returns then?
Really far away.
Really far away.
In the next room.
Low,
That is not the answer. So somebody give me something else.
low,
Low, that could be an option. Yep, that's one. What's another one? This one's less intuitive. How would you?
Yeah, there's an answer on that.
Justin has an answer. I'm not sure what it means. It says in line with the supplies.
Aha, that is the answer. Tom doesn't know what that means.
Oh, that.
Look at that. Yes. So yes, you could put them, or a really good design, what we recommend is putting them in line with the supply. You would have a supply section, maybe an inactive section and a return section. So from the room side, it's this really nice, beautiful continuous slot that makes the occupant feel really nice, but above, we know that we've got some variability in the slots. If we're supplying out of one section, it has no choice but to make its way into the room to get kind of pulled back up into the middle. So this is the best design for slot diffusers here. Whoever that was, they get 2 points. All right. Look at that. Beautiful arrows. Slot diffusers I mentioned are really nice for architectural spaces. So you can do fun things, with the mitered corner to keep it this continuous look. Or we can even curve the slot diffuser. So in this bulkhead right here, it's a little hard to see, especially on this screen right now. But that bulkhead does a little bit of kind of waving, and you could put a slot diffuser in there that matches it, whether it's concave or convex. You could also take a slot diffuser and curve it this direction. So maybe on a ceiling, you've got a wavy bulkhead that you want to match the curvature of. You could do all of that with curved slot diffusers. So very architecturally friendly. Smoke video of the slot diffuser. So the one here on the left is our horizontal throw across the ceiling. They do travel pretty far. Slot diffusers have a pretty long throw because they are coming out at one direction. And then your vertical throw. This would be an example of washing the window. And you can design that throw to come down pretty straight and vertical like a rectangle, or you could throw some angled baffles or an angled plenum on it and have an A-frame shape come out of the diffuser. So couple of different ways to wash the window. Linear bar grills. So linear bar grills usually used kind of in 2 places, either sidewall, usually high sidewall grills, or on the floor. Linear bar grills, similar to a slot, you're gonna have the plenum behind it, but they are more visible, usually a little bit bigger, and have cores on the inside. So there's light duty version and heavy duty. Can anybody guess where you might use a light duty versus a heavy duty?
light duty on a pedestal, heavy duty on the floor.
Perfect.
Mandrel if you're gonna drive a truck on it.
Yeah. Yes, the mandrel is just much stronger than the pressed core, but both the heavy duties can go in the floor. There's an example there of the back of it, so you can actually see what that mandrel looks like. And here's what happens if you try to put a light duty in the floor. Probably would not want to be walking that. So we need those supports of the mandrel to put any bar grill in the floor. All right, I told you we'd come back to throw. Coanda effect. It's a really fun word for a pretty simple topic. Coanda is, I'm gonna get the actual definition wrong, but it's the phenomenon that a liquid gas is going to stick to a fluid, thank you. It's gonna stick to a surface kind of as long as it can. So when we're talking about ceiling diffusers, we looked at all those smoke videos. The smoke's gonna come out of the diffuser. It's gonna run along the ceiling for a set amount of time before it kind of releases and starts dropping into the space. We want coanda, especially in ceiling diffusers. We want our air to travel across the ceiling before it drops. Keeps us from having draft points in our space. But in order to kind of maintain coanda, sorry, that's not what I was meant to say. The throw distance that's cataloged from a diffuser is assuming coanda. If we don't have coanda, we will see that throw distance reduce by about 30%. So if you have a black, let's assume that speaker right there is a diffuser and it was releasing into this space without a ceiling. It will throw out horizontally, but it has nothing to stick to. So it's going to start dropping into the space much faster. That means our throw distance will be 30% less than what the catalog is showing because we don't have a ceiling. The same thing would be true here with a sidewall grill. If our sidewall grill is so low that it's not going to catch onto the ceiling, the throw distance will be shorter than what is cataloged. And what that distance would need to be, if you're 18 inches away from the ceiling, then it won't latch on.
This is the same effect as what all the aeroplanes get the lift off from the ground. This is the change in the pressure. So when they are in the runway, they create a coanda effect and then they take the lift off, they go up in the air.
I learned something new today.
To say it
Well, it's a good
backwards.
time. You can just say whatever you want and get a ticket now.
Now, this is change in static pressure.
Yeah.
It's change in static pressure, right by the wing. If it's on the plane, it's, for the grill, it's just a change in static pressure.
All right,
He's laughing.
I'll come up and give you your ticket in a minute.
That's not for the ticket.
Coanda and obstructions. Usually we can design this beautiful ceiling and all of our airflows could work perfectly fine. And then a sprinkler head gets dropped or an exit sign or a lighting fixture. All of these are different obstructions in our ceiling that are going to affect the airflow pattern across the ceiling. If that obstruction creates a greater than 10-degree angle from our airflow jet, then we will have an issue. If we're less than 10 degrees, we won't. This is better explained with this smoke video. So here, no, just stop.
Well, it's kind of the same as your grill area
Here we
thing.
go.
It's
Here we go.
Same as an obstruction.
So this is our supply diffuser. This black piece right here on the left is our deflection or our obstruction. In this first video, it's only an inch long, or yes, an inch long, tall, an inch tall. And we will see that air just kind of pass right over the obstruction without any issues. Tugging to the ceiling, performing exactly like we would expect. Now, if that obstruction were 3 inches, a little bit longer, and that angle is greater than 10 degrees, we are actually going to see the air drop from the ceiling and shoot straight into the space. Imagine if your desk was right here. That would be awful. Just be blasted with cold air all day. So that obstruction is not allowing Coanda to happen. It's forcing the air in a different direction, which is down into space. That room smelled up pretty cool. Play one more time. You can see that dropping. So, could be something like a lighting fixture, an external component, but it could also just be a bulkhead in the ceiling. Often in restaurants, I feel like restaurants are the most drafty places ever. And it's probably, if you look up in the ceiling, you're gonna find some type of obstruction that air is just hitting and coming down. So something to be mindful of in design. All right. Kind of bringing Thoreau to an end here. Closing off Thoreau. All of the cataloged Thoreau performance is based on isothermal conditions. For a ticket, who can tell me what isothermal means?
Oh, come on.
Isothermal. Not Tom.
Ooh, any chat people? No chat.
Because I'm keeping the ticket there. Isothermal means that our supply air temperature is the same temperature as our space. There's no difference, there's no temperature difference between the supply air and the space. Almost never or very rarely are we supplying air into the space at the exact same temperature as the room. We're usually either actively cooling or actively heating. So we're either gonna have 55-degree air in a 75-degree room, or it'll be 90-degree air in a 75-degree room. So if all of our catalog data is based on isothermal conditions, we're never actually performing there, what is gonna be the result in our space? In heating, if you're heating horizontally across the ceiling, you're gonna get a Thoreau length that is longer than what is cataloged. That's because hot air likes to stay high and hug the ceiling. So the rule of thumb is a 1% increase per degree difference. So if our space is 75 degrees, we're supplying 90-degree air, you're gonna see a Thoreau increase of about 15 to 20%. So in heating, it will get longer. What happens in cooling? It's shorter. Yes. So the exact same rule of thumb is true. 1% decrease for degree difference in temperature. So our throw length in cooling is shorter than what is cataloged. The opposite is true if we are throwing vertically. Because in heating, again, our air wants to stay high and hug the ceiling. So in heating, we will get shorter throw distance compared to catalog. And in cooling, we will get longer. Cold air is heavy and likes to fall. Here's kind of a summary of that. When you're shorter in cooling, longer in cooling, etc. Usually, I would say engineers are not probably designing with all of this in mind. But
Suppose if you hit the wall and drop, it's a wash.
yes,
Right.
yes, yeah. It really might become an issue in weird situations where you've got two diffusers really close to each other, or a bulkhead or an obstruction or something that wasn't properly accounted for. All right,
We're at a little bit past 12, so
we are.
we have fulfilled our requirements. How much do you have left?
This is the
Only
last.
60 slides.
This is it. There's the summary.
Okay,
I'll take 3 minutes.
sounds good.
Okay, Purity sound. So all those diffusers are cataloged, assuming one diffuser in the space. We very rarely have one diffuser in the ceiling. And we're also assuming a room of this size, 20 feet by 20 feet. What happens if we don't just have one diffuser, we have 4 diffusers? What actually happens to that sound? So per catalog, let's say one diffuser has NC 25. The result of adding 3 other diffusers with NC 25, so we've got 4 total at NC 25. they're not additive. We don't now have NC 100 in the space. We're gonna use this rule down here. If we've got multiple air outlets at the same NC level, we are adding only a small number of kind of boost to the sound. So overall, our one diffuser at 25 went now 4 diffusers at NC 31. NC is a log, or sound NC is a logarithmic equation, so it's definitely not, sound source A plus sound source B equals C. A little bit more complicated than that. And then what about distance from the sound source? We've got now this kind of grumpy businessman sitting in the middle of this room. How is he going to perceive the different sound sources? Well, we are usually always assuming that a person can only hear sound sources within this 400 to 600 square foot room space, so our 20 by 20 room. If we've got a larger room, maybe a big open office space with diffusers all the way down to the other wall, a person might be able to hear a little bit of the diffuser outside of that 20 by 20 space, but they are absolutely not going to hear a diffuser all the way across the room. So the diffuser right outside there is probably negligible. We're usually only concerned with the sound of our occupants within that 20 by 20 square foot space. And then my final point here, dampers and how it affects sounds out of a diffuser. So again, all the catalog performance is just a straight diffuser, no damper on it. But often we have to add dampers in the field. The rule of thumb is put the damper as far away from the air outlet as you can. If you're putting an diffuser right at the air outlet, as shown here and on the back of that register there, you are now adding or changing the velocity of the air right at the outlets where the occupant can hear it the most. So you're going to see the biggest increase in sound. As we start to move that damper a little bit further upstream, we can cut down that sound generation to nothing if we just get it out of the actual diffuser itself. All right. I'm not gonna repeat myself here. That is it for everything today. Are there any other questions? Or a ticket? Any questions?
Can I have a ticket? How about a nice hand for Elizabeth Turner? And thanks to everybody who watched remotely, and thanks to everybody who came today, and we'll see you next month.
All right, so everyone who's remote and asks a question, I'll send them something, but for everyone in the room, go ahead and draw these real quick.
Oh, and lunch is served.
Lunch is behind me. Okay, so what we got here? We have Camelback insulated little mugs.